Good morning, everyone. I hope you had some rest and the opportunity to go around a little bit. And, well, before we start, let me tell you that today we have a visit to some of our labs. And later on, we will give you details about that visit, okay? But for now, I'd like to invite Professor Alexei Maidibaev. Professor Maidibaev is originally from Russia, but he is living in Rio. I don't know how long have you been in Rio, Alexei? 10 years, okay. And he got his PhD degree and also the Doctor of Science degree from Lomonosov University in Moscow. And I am sure that he will give you a very nice talk. So let's receive Alexei. Thank you very much, Alexei.
Thank you very much, Carlos. Well, thank you everybody for coming. Thank you, organizer, very much for organizing this very interesting event. So, okay. So I'm Alexei, and I'm coming from IMPA, which is Institute of Pure and Applied Mathematics in Rio de Janeiro. So, which this means that I will teach you some mathematics. No? Focus of my talk is of the mini course is parametric resonance. This will really be very classical basic things, which I think will be important. So we will start by deriving equations, analyzing equations, finding solutions. But by the end, we come to the serious things. Those will be experiments and all these kind of things. So just be patient. Okay. So there are notes, and you can find them on my web page. So if you enter the web page, it's very simple. It is alexei.impa.br. So if you see here, no, at the top. So you enter to this page, and then go. There is a pointer maybe. If okay, no, don't worry. So and then you go to this teaching where I used to go to put this material. So I just put it yesterday. So you have a lecture notes. You have a lecture notes. So you click on it, and you get up. Yes. So you go down, and then there is essentially most of the material is here. So it's convenient. Okay.
This is just a pointer.
Oh, this is very much. No, this I prefer to. Thank you very much, Carlos. Okay. So what is parametric resonance? So I will start with some videos. So let's, as I said, that we will come to the, first of all, what I would like to know. Because I will derive equations, and there will be some mathematics, which from our point of view, mathematician is not that much advanced, but also not so simple. So I just so the auditorium is who are engineers? Okay, okay, who physicists? And mathematicians? Good. So it is good, will be useful. Will be useful. So I'll start with a simple, very useful application, which makes shows exactly the difference between usual resonance and parametric resonance. So the usual resonance is this first link on YouTube. I spent some time yesterday to look for them. So where is sound? Sound here. No, it's okay from computer. No, it's okay. No, it's okay. No. Okay. So this is the first application I found yesterday. So she will show how to swing. So this is a swing. Don't hear. Maybe we put connection to the audio. Only make it less. So you see, this is resonance. Yeah. So why is it resonance? She does a motion in the same frequency as a pendulum, and essentially what she does is a horizontal shift of the mass. Yes, which give a torque, which is exactly the same frequency as the pendulum, and quite successfully increasing the amplitude. So essentially what she does is she destabilizes the vertical equilibrium. So, well, now it will be, she represents a dog, so this is out. This is already not important for us. So, okay, this was about small pendulum. If its pendulum is large, I learned that probably this kind of toy was also only existed in Soviet Union. So that when they have a very big swing, it's sometimes even kind of in the form of the ship. So then you can try to swing it. So you cannot do it like this because it's heavy, it's big. So how to swing a big swing? So this is another video, which is from apparently from Estonia, because it is in a sense this. So you see the swing is much bigger, no? And what he does is totally different. So you see he's sitting on the middle, standing on the top, sitting on the middle, standing on the top. So he's not following frequency of the pendulum, his frequency is double. Because he does the same motion every time the pendulum has a half a period. And then the same motion another half a period. So his frequency is double of the frequency of the pendulum. And you see he's very successful, no? It should be seen to the end. No? Don't repeat. You did full circle. I kind of remember I did it in my childhood, but I cannot. When I look at it. Okay, so we can switch it. How do we switch it off? Maybe it will. Okay, let's.
So the new World Guinness record for the kicking is 7.15 meters.
Oh, because it goes to another.
It's typical for Estonian sport.
So let's just. Yes. Okay, let's just close it. Okay. So, here's my notes. So let's put a very simple model to this problem. Okay. So what will be the model? What essentially we saw in the last video? So he's sitting and standing. Sitting and standing on a pendulum means that he's changing the length of the pendulum because he's moving mass up and down. So essentially it's changing length of the pendulum. It's slightly a more complicated problem. So what we will do, we will shift upper point of the pendulum. So we will shift support of the pendulum up and down. So this is a model we consider. So assume that you have some support of the pendulum. I have to, let's see which is better. So, and then, okay. The pendulum with a mass, certain mass m, length L, there is a gravity. Let's put gravity on the left. There is a gravity, and there is angle. So every position of the pendulum is defined by the angle. Problems to see? No, you don't see anything. Ah, you see, okay. So what we will do is we will put this support up and down. No? So support up and down will be, some position of the support will be h with the function of t, and it will be periodic. As we read, so with the period t. Okay, so period t and frequency is omega. We know it's 2 pi over t, angular frequency. Okay, so let's first write a equation of motion. So in order to write equation of motion, we put axis, so it will be x-axis and y-axis. And first, let's write coordinates of this of the body. So the coordinates of the body, I will use more. So x coordinate of this pendulum. Let's also clean it. No, I don't think it will help. So the horizontal coordinate is length of the pendulum multiplied by sine. Yeah? Easy. So the vertical coordinate is L multiplied by cosine. So L multiplied by, well, we can subtract, depends on where you start to compute. So let's compute it from position of the pendulum. So it will be 1 minus cosine phi. And then you should also add the position because it is relative to the position of the support, so you add support. Okay, so then speed. Speed, you just differentiate everything in time. So it will be cosine, L cosine phi, and in the chain rule, so it's phi dot. And then when you differentiate y, it's L cosine. Cosine will give minus, so it will be L sine phi dot, and h is time dependent. So apply it's h dot. Okay, So now with this position velocity, we can write equations of motion. And equation of motion, we will write from Lagrangian formulation, so you need a Lagrange function. Lagrange function is kinetic energy, potential energy, and the physicists know the sign. No? Oh, okay. So probably this course is not is very, very basic for you. So okay, minus. And kinetic energy is mass over 2 over by the squared velocity. And potential energy is mass, gravity, vertical position. So we have everything, no? So we have everything, and just substituting one to another. And then the generalized coordinates, there is just one coordinate which drive everything, because when you substitute, you will get functions, so Lagrangian will depend only on angle and angular velocity. So then you will get equation of motion, which is Euler Lagrange equations. Lagrange. I need to use 2, so and change from time to time. Euler Lagrange equation. An Euler Lagrange equation, well, maybe physicists know it more like Lagrange, no? But we're mathematicians. Euler did it way before. So it's a time material derivative by the partial derivative of Lagrangian with respect to the speed minus partial derivative of Lagrangian with respect to the phi equals 0. And then what remains is to substitute and compute. So let's first write Lagrangian. So Lagrangian is, we substitute these two formulas. So m over 2 L square cosine square phi dot square. Okay, so x dot square plus y dot square, so it's plus, I already open square, so L square sine square phi dot square plus 2L square, no square, L sine phi dot h dot plus h dot square and minus mgy, so this business, mgl 1 minus cosine phi and minus mgh. So now you can simplify your life by noting that what enters in the Lagrange equations, so these are equations of motion, are derivative of Lagrangian with respect to angle. So this term does not have derivative, so we can forget about it. It has no derivative. This had no derivative. No? So just remove, because if you put or remove them, this equation will not change. Okay, and you should remember that cosine square plus sine square will give you 1. So you get L is m over 2. So what is remaining? So L square phi dot square, and this term plus m L sine phi point point, h dot, and then plus mg L cosine phi. And we're done. Let's double check. Well, everything is plus, so good. Oh, and now we substitute this Lagrangian to the formula. So first term is a material time derivative by the derivative of Lagrangian with respect to phi dot. So phi dot comes here and here. So we differentiate it with respect to the speed. It will be m over, no, there will be not 2. So it will be m L square phi dot. And the next term will be plus ml sine dot. Good. And then minus the LD phi. So what is the derivative of the LD phi? So where the phi enters? Phi enters in two positions. So phi enters here, the phi enters here. No? So these two terms we should differentiate. The derivative of sine is cosine, derivative of cosine is minus sine. So ml cosine phi dot h dot and plus m g l sine phi equals 0. So let's divide it everything by m L square. So what will remain? So here will remain phi dot two dots. Now you have to differentiate with respect to time. So this is important that this is material derivative. So this is derivative which assumes that all variables are time dependent. So this is time dependent and this is time dependent. So the next term will be plus ml cosine phi dot h dot and plus ml sine phi h double dot. Okay, then we have this term, so it will be yeah. Okay. Yes. So we should get this, and yeah, good. So here it will be minus 1 over L cosine phi dot h dot. These two will cancel. And then will be plus g over L sine phi equals 0. And then we finally get to the equation phi double dot plus, so this same sign. So let's put g over L outside. And then it will be 1 plus acceleration of the support divided by the gravity acceleration. Sine phi equals 0. Nice. So it's good to write So it's good to write equations of motion. So let's start with this. So this is, we derived the equation of motion for the pendulum with the moving upper support. And the motion of the upper support is completely here. And somehow, if you're a physicist, you kind of see that G by this, it will be G by H double dot. So it's actually correction of the gravity due to acceleration of the base. So you maybe could guess this equation from the very beginning. And if there is no support is static, so there is no this term, then we already know that the natural frequency of the pendulum will be given by this coefficient. So the frequency of the pendulum is square root of G over L. So the nice thing, it does not depend on mass. So whoever you put on a swing gives the same frequency. Okay, so now we are going to study this equation. So the next step is we will derive some theory which allows to solve these equations. So the first idea, in order to make any theory, so the first step is to write this equation as something more general. So what we do is first we reduce this equation to the equation of the first order. So what you do, you say that now the angular velocity, we will call it with a new variable, psi. If you call it with a new variable psi, then this equation can be written as psi dot moving everything to the other side. So it will be psi dot equal minus j over L 1 plus h double dot over g sine phi. And then we form the vector out of these two, so it's two-dimensional vector. And then two equations can be written as a single one. So y dot equal this is not gravity, so it will be both. G of yt, where, so what is G is, so you see that y dot equals some function, so first component is psi, and the second component is psi dot, so it should be this minus j over L. So in this case, and what is important for this equation is that this equation has two properties, which will be important for us. So the most important property will be that there will be two properties. That this equation has equilibrium. Okay, no. So now we are going to study this type of equation. So this is a general ordinary differential equations, which is time dependent. So the general ordinary differential equation with the right hand side, which depends explicitly on time, and what will save our life, the dependence is periodic. So this dependence of time in this function, it sits here in h, because it was a position going up and down. So there is explicit dependence on time of the function, but it's periodic. So how one solves this kind of equation? So let's repeat. Y dot equal j yt. In general, most of the in general you consider that y is vector that collects all your coordinates and all your speeds. So it has some dimension n. The next thing that we will assume is that g is a periodic function. So if you add some constant period, it doesn't change. And then we also assume that we have equilibrium state. So let's call it y star, which means that there is a solution which is just constant. What means it's constant? That derivative with respect to time to be is 0, which so this is equivalent to assume that g is 0 for any time at this point. So we will study this problem. So the difficulty of this problem is that there is no explicit solution to this kind of equations. They're extremely complicated. So the very useful tool is which simplifies slightly this equation, is to introduce what's called Poincare section. Poincare has an accent in this direction. Poincare map. So what is Poincare map? It is the following. So let us study this evolution of this system. So we will put time horizontally and y vertically. So this is our coordinates. So let's say y1, y2. So this is this here is y plane, and then horizontally will go time. So the solution is some curve. So you start at some initial condition at initial time, and then you integrate this differential equation. So it's some motion. So it turned out that it's sufficient to study this motion not at all times, but also only at discrete times. So what are the discrete times? Are the times which spaced in a period. So let's put 1 period, 2 periods, 3 periods, and so on. And at each period, we can look at our plane. So the phase space. And see where the curve comes this time. So now what we will do, we will say that we will only look at this point. So is what Poincare map means that instead of looking at the evolution of your system continuously in time, you have a camera. We just take pictures at equally spaced times. And this spacing is exactly matched to the period of the system. And why it is good is because system itself is periodic in time. So the evolution from this map, this plane to this point is exactly the same as evolution from here to here, and so on, because the right-hand side of the equation in this interval is exactly the same as in this interval, and so on. So the right-hand side is periodic. So there is no the evolution, the rule which connects initial point to the final point. The first period is the same as the rule connecting this point to this point and this point to this point. So we put notations. So we say that yk will be value of y at k periods. And since we have a system, so y at period t, so which is y1, is uniquely given by the y at the previous time, because it's a differential equation, so it has a unique solution. So we say that there is a function f which connects to initial condition, or in other words, connects your photo at y0 to your position at the photo at y1. But as I said, the rule how you connect the points is the same every period. So there is a, at hk plus 1 photo, the rule will be the same. It will be linked by exactly the same function to the previous point, and this function f is what's called the Poincare map. So the Poincare map is the rule which defines the change of the state at one moment to the state after period. And of course, what means fixed point? So there is we have an equilibrium. So the equilibrium means that equilibrium state should not change. So in the equilibrium is the rule which tells that Poincare map does not move this point. So it's good to draw it. So the equilibrium solution is a straight line, and it goes for exactly the same points at each Poincare section. And so on. So it's a fixed point. I thought it will change, so okay for this. So okay, good. Well, we seem to be okay. Okay, so this is this made it simpler somewhat. Not too why it made it simpler? Because now instead of the differential equation, which we have to solve in time, we have just algebraic equation, which is you just have to apply the map. So if you know how to compute the map, you just apply it, and then you know what happens at each point. So, but still, the dynamics of the maps is extremely complicated. So the next step to do is called linearization. So let's recall what is regularization. Well, I'm giving rather, I'm sure for many this is rather elementary stuff, so if it's very easy for you, probably for, I hope it's not elementary for everyone. Okay. So let's remember what is linearization mean. So linearization means that we want to study the solution near equilibrium. So, which means that we will write our vector y, which for the pendulum it is, remember, angle and angle velocity, so it will be y star plus x. No? So x is a perturbation. It's a vector of the same dimension, and x is small. x is small. I think what means small, I should not explain to physicists, engineers. No? And if it is small, what we can do is we can use a Taylor expansion for the right-hand side. So we will Taylor expand the right-hand side. So we take the function g, and we substitute this expansion. And we Taylor expand with respect to x. So what it is? So it is value at x0 plus, so if x would be a real, I would just write derivative. Remember, so derivative gx, dx, and multiply by x, but x is a vector, so it will be a matrix. So it's a Jacobian matrix. So I have to put a matrix. I'll tell in a while how it depends on time, and multiply by x, and then there is a higher order term. So what is g is actually derivative of j of all components of j with all components of x. So this is what's called Jacobian matrix. This is dg1 over dx1, dg1, g. Well, you can differentiate with x or you differentiate with y, it doesn't matter. No? Let's write y. It will be dg2, dy1, dg2, dy2, etc. So this is called Jacobian matrix. And it is computed at y equal at the equilibrium. Yeah. So now remember that at equilibrium, this is 0, right? Because I wrote that this is a condition for equilibrium, that j is 0. But derivatives are not. And since g was periodic, g was periodic, so its derivatives are periodic function of time. So that's why I wrote t here. So since everything is periodic, g is a periodic function of time with the same period. So this is n by n matrix. So the linearization means that we now take our equations of motion and substitute this and this. So the derivative of y, this is constant, so it will be x dot. And g, the first term is 0, so what will remain is linear term. And now I will neglect the small terms because I assume that x is small, so this is small. So this equation is what's called linearized system. Good. And now, okay, so let's just quickly see what it is. So for the pendulums, it is useful. So the pendulum G was phi psi, and then it was minus G over L 1 plus H double dot over G, no? Sin phi. Y is a vector of phi and psi. So what was the equilibrium? Equilibrium of it was a vertical position of the pendulum looking down, so everything is 0. So Y star was 0, 0. And you see that already we put 0 here, we put 0 here, so G is 0. So we verify this condition that G is 0. And our Jacobian matrix will be, so with respect to, we have to differentiate with respect to phi and psi. So he's only psi, so it will be 0, 1. And on the second line, it's only phi. So it will be minus G over L, 1 plus H double dot. I will write explicitly, it depends on time. And cosine phi, 0. But now we have to compute it at the equilibrium. So which means that psi is 0 and cosine is 1. So this goes to become 1. So we have a nice matrix, so 2 by 2 matrix, so this is I remove. This I remove. And you see there is 2 by 2 matrix, and it depends on time because we have this position, vertical position of the support explicitly here, and it is periodic in time, so everything is periodic in time, so it works. I never give lectures for 2 hours. I always give interval after the first hour. Then you, question. I will not continue before anyone asks a question. Because this means that nobody understood anything. Nobody didn't. Okay, I will ask a question. So what next? Eigenvectors. Eigenvalues. Oh, good. So we will have to come to eigenvalues, eigenvectors, but we cannot because still so far it's time dependent. Good. So we have to go to something which is not time dependent to have eigenvector. Well, let's make a break. So I will show you video. Just for you not to think that this is the theories applications. I will show you the application which is way more than this at the end. Oh my God. Wait. I don't know what happens. Okay, good. Oh? No. We will take a 2 minutes rest. No? That's parametric resonance for a ship. And this is very much like pendulum. So it's going up and down. There is this, so just instead of support from above, it's support from below. So going up and down. And the parametric resonance is between this frequency of the waves and the rolling, so it's not this motion, but this. You see, actually the wave amplitude did not increase a lot, but the amplitude increased quite a lot of the ship. I also found yesterday some video. Yeah. This is very funny. So, but anyway, this is also parametric resonance. So you see, he's sitting and standing. Exactly. So with this double period. So, and you see how efficient it can be. So in the first video, it was bad for the ship. Now it is good for the kids. I think it was from the time when now it's made by the motor. No? But it was, in some places, still mechanical devices remained. Good. Okay, so the next. So next we, at certain moment we should come to the eigenvalues. So how we go to the eigenvalues? We have to make linearization not for the original system, which was a continuous time system, but we have to make a linearization for the Poincare map, which is discrete time system. Because in Poincare map, instead of time, you have this k index. And k computes how many periods of time you progressed. Yeah, so k is time in that sense, but it's discrete because it's only takes value 1, 2, 3, 4, 5, so on. So we have to make a linearization for the Poincare map. So this is what we're going to do now. I will rewrite these equations on the top. So for the Poincare map, we have a discrete time system. Which is integer, so it's 1, 2, 3, 4, 5. And the system is that the position at the next period is given by the Poincare map from a position of the previous period, And we know that the Poincare map does not move the the equilibrium. So there is difference in a continuous part. G is 0, so but in a discrete part time, f is not 0; it's the same value. Question? Yes, good. Sure. Yeah. Very good question. So this is exactly the point, because both position and displacement are not periodic in time. But what is periodic in time is the right-hand side. Yeah. So what is repeats itself after each period is the law of motion. You see, the motion itself is not at all periodic in time, but law of motion repeats, which means that when you move from k periods to k plus 1 periods, the law is the same. But the motion every time is different. You see, no? Yeah. So this is the whole idea of the Poincare map for this periodic time system. Okay, thank you. So we do the same stuff. So we write k yk equal y star plus xk, which is a displacement, which is small. Xk small. And then we expand f in Taylor series. So f at yk is at y star plus x, and now we expand it in Taylor, so it is f at y star plus, again, this linear term, so matrix of derivatives. We call it f by x, k, no? K, and high order terms. So now f is what? F is a matrix of derivative of f with respect to the components k1. So the matrix of which contains a derivative of all components with respect to all components of y, just in the same way. But this matrix is time independent because f is time independent. So this is just constant matrix, n by n matrix. Okay, so we substitute these two into the equation. So what you get, so for the first it will be y star plus xk plus 1 equal this, which is, this term is y star because this is equilibrium, plus f xk, y star cancels. So what we get is we get discrete time linearized system. So this is the linearized system. With a discrete time, and now it's time independent. So this is essentially the trick. So now we will be able to find eigenvalues, but before computing eigenvalues, let's make a connection, because our original system is continuous, and this is just a construction which made on top of it. So how to compute f? So by the way, f is the Floquet matrix. Floquet is French, you know, so it doesn't read how it writes. So that's whatever. Okay, so let's compute the connection. So in order to compute the connection, we should find matrix F. So the two systems by construction are equivalent, no? Because they were constructed equivalently from the same solution. So what must be is that xk should be exactly the value of the solution x with continuous time at k periods, right? Which means that if we take k equal this equation with k equals 0, which means that x1, which is just x, let's take this equation for k equals 0, so x1 equal f x0, and this is the same as we take left part is x of a time t in a period, and it should connect it with x at time 0. So we should find a matrix which links initial condition to the one period condition for that system. So x now satisfies this system. So this make a connection between discrete time and continuous time. So now x is a solution of the system. Okay, so the way how you compute it, and there is a way which which is convenient for computing numerically, for example, because this is exactly the matrix you will need, and it will define all the. No, it's not. It's not YouTube. No. Okay. So it's outside sound, no? Yeah. Okay. Good. Thank you. Okay. So the convenient way is through a so-called fundamental solution. So how you construct fundamental solution? Fundamental solution, take instead of the vector x, take a matrix. So consider so it's capital X, which will be n by n matrix, which will depend on time and such that which will satisfy exactly the same equation. So we can write for this matrix exactly the same equation. So it's okay because this is n by n matrix. N by n matrix product of two n by n matrices, n by n matrix. So this gives this derivative. So this is n square differential equations. And we have to put initial condition. So we put initial condition at 0 to be identity matrix. Identity matrix, you know, it's matrix which has 1 at the diagonal and 0 outside. Okay, so this is what's called fundamental solution. And this fundamental solution you can compute numerically, usually for any system, because whenever you are given initial system with giving this small g, you can compute capital G, which is just Jacobian matrix, derivatives, and then you have to find the solution. You can find solution of the system just numerically. And you don't need to find it for a large time, because we will see that it's only sufficient to find this solution at one period. Why? Because how we can compute. So now let us consider x. So what we can do is we can multiply. So this is matrix. So we can multiply both sides by initial condition. This is this construction, no? Probably. So we can write equation. So now you see this is a vector, right? Because we multiply matrix by a vector, so it's a vector. Which satisfy the same equation. And now, additionally, at initial time, so if you compute it at time 0, this is identity. This is identity by x is 0, x 0. So if you know fundamental matrix, you automatically find the solution of your equation with any initial condition by multiplying this fundamental solution by initial condition. So it's a way to produce any solution. This is why it's called fundamental. And all we need to know is to find x at period, which means that x at period will be fundamental solution at period by x at 0. But now you compare this equation with what we wanted to find, and we see that f is exactly this matrix. So the Floquet matrix is a fundamental solution at one period. So I will encircle it in red. So from practical point of view, it's done. Yeah. So in order to find the Floquet matrix, which we will see, will define everything. You can solve your system with respect to one period, in one period, which is okay. So most likely it's impossible to do by hand, but it's certainly not difficult to do numerically. So this is what people usually do, and you don't need long time simulation, just one period. So one period computation gives you the Floquet matrix. Good. So our next step is that we reduced the dynamics of the perhaps complicated system, nonlinear and so on, to the dynamics of the Poincare map, which is linearized near the equilibrium. So it's essentially just multiplying your state, your deviation by matrix. And we know how to compute the matrix. So you just multiply the state by matrix. So we get a linear discrete time dynamical system. So you just, if you know initial state, you just multiply by matrix, you get it after period, multiply by the same matrix after 2 periods, and so on. So we will analyze, so the behavior of the system near the equilibrium, and essentially what will be interesting is the stability issue, and instability, which is a parametric resonance, will be determined by the properties of these dynamics. So now we will find explicitly what the dynamic is. The next subtopic. So linear discrete time dynamical system. Which is exactly what this is called. So how to find solutions, and we already had a comment how to find solutions, eigenvalues. So eigenvalue problem. So we have to write eigenvalue problem. So we'll write eigenvalue problem for this matrix F. What eigenvalue problem means is that you have to find vectors, which are called eigenvectors, which when you multiply this vector by matrix, you get a vector which is the same vector u, but multiplied by the constant. So u is a vector. It's called eigenvector. And rho is a scalar. No, and everything is complex, which is, we will see why. So everything is complex. Everything can be complex. So this will be eigenvalue. Okay, so before solving the system, let's see what this will give us to us. So assume that we have one pair of eigenvalue eigenvector, and we take initial condition. We take initial condition to be exactly eigenvector. So what will be the dynamics? Because x1 is f of x0, but f x0, so this is x0, no? Is f by u, and f by u is rho u, right? So when you do it again, you multiply again f by u, it will be rho square. So, which means that uk, when you do it k times, every time you do the step, you just multiply by rho. That's why these eigenvalues in the Floquet theory also called multiplier. So rho is eigenvalue, and also it's called multiplier. Because it multiplies solution every time. So now so this is the solution. This is a solution if rho is real. Because if the multiplier is real, eigenvector can be always chosen to be real, so this is a real solution. So now I said that eigenvalues will not be necessarily real, so they can be complex. And what do we do with the complex eigenvalues? So if rho is complex, which means that it has an absolute part and it has a phase, complex phase. What I use, phi, no? So complex phase. So in that case, okay, it's still a solution, but it's a complex solution of our dynamical system. But what is important is that first of all, this system is linear, and all coefficients are real. So whenever you have a complex solution of the linear system with real coefficient, you can separate real part of the solution and complex imaginary part of the solution. Each of them will be the solution, because each of them satisfies, they don't talk to each other. Yeah. So then, which means that real part of the rho ku and imaginary part of rho ku are solutions, are real solutions. And it's actually not surprising that you get two solutions instead of one, because whenever you have a solution with rho of the eigenvalue problem, which is complex, you automatically have the solution with rho complex conjugate. So the eigenvalues are also come in pairs. So it's not surprising that solutions come in pairs. And let's just write what it is. So we have to take real part of this stuff, and remember that rho is this. So the solution, one solution. So the solution one is xk, which is a real part of rho ku, but rho ku is absolute part power k, exponent k phi u. But u is also complex, so we take a real part of this combination is will be real part of u by real part of exponent, which is cosine. And then it will be minus imaginary part of u sine. And then the same way solution 2 is imaginary part of the same stuff, and there will be slight difference. The imaginary part is you take real part of this to the imaginary part of the exponent, so it will be a real part of u by sine k phi, and plus imaginary part of u cosine k phi. So we get explicitly two solutions in case of complex eigenvalue and one solution in case of real eigenvalue. Oh, we're good in time. So the last step is how do you solve this problem? How do you solve eigenvalue problem? Eigenvalue problem. So we need to solve eigenvalue problem, which is to find vectors and scalars which satisfy this equation. And how you do it, you put everything to the left-hand side. So you take rho f minus rho u, but rho u you can write as rho identity u, so it will be minus rho identity matrix by u equals 0, because this is will give u. And then you know that if u is not 0, because 0 solutions we have no interest in 0 solutions, then this matrix should be singular, right? So, which means determinant of this matrix is 0, but determinant of this linear combination is a polynomial. Is a polynomial of degree n, which gives us n solutions. And complex solutions. So in principle, we can get n complex solutions out of this determinant. They can be multiple, so they actually can be repeated. We will see it in a while, but so let us assume that all of them, all eigenvalues are different, so are distinct. So let's number them. We have n of them, which are complex. And so we assume that they are distinct. Or in that case, in linear algebra, they say it's simple. So they're simple. Let's assume that all of them are simple, which means that for each of them, you can write a solution. So for example, if they are also real, you have a solution in that form for each pair of eigenvalue, eigenvector. So each xk equal rho k uk. So each eigenvalue comes with eigenvector. But now each solution you can multiply by arbitrary coefficient. So this is k, this is j. So we have a j solutions, with j is from 1 to 3 up to n. So at time k, you can find a solution. You can multiply by arbitrary coefficient, it's still solution because it's linear. And you can sum up over j, over all eigenvalues. So what I claim that this is a general solution. So this is a general solution for our system, for our system xk plus 1 equal f xk. So I claim that this is exactly give a general solution. What means general solution? That I can construct solution for any initial condition. So I can find this coefficient Cj and give a solution for general condition, and so it will give explicitly value of the dislocation each k whenever we know initial condition, which means whenever we know coefficients k. Why? Because for k equals 0, which means time equals 0, k equals 0 removes these powers. So x0 is the sum over all modes Cj, Uj, but U1, Un is a basis, in the Rn space if all eigenvalues are simple. So what we assume that they're all distinct. So this is a basis, which means that for each initial condition, you can choose coefficients. Knowing coefficient, you substitute it here, and you know solution for each time. So you explicitly found solution for each time. And if rho is complex, if any rho is complex, just use this real imaginary part trick. So use this, instead of those solutions, you just use these two solutions. And that's it, because it will be still n solutions. So we found an explicit solution, and let's make there are several examples that I want to give. So let's just compute explicit examples how you find this solution for some real explicit matrices. Question? So why we do have the same amount of solution if we have in a complex case? So if rho is a complex, what I claim is that still I have n independent solutions. So why is it so? Because okay, so it's not so easy. So because when the rho is a complex, there are two together with rho, you get a complex conjugate rho. So out of this sequence of rho, so to each complex value will be a complex conjugate, which comes next. So there will be two of them, and you also for this pair you will get pair of solutions. So the number of solutions is the same. So we will let's see the example. Example. F is 2, 1, 1, 2. Eigenvalues, so we need to write a characteristic equation, which is this determinant. So it will be 2 minus lambda, 1, 1, 2 minus lambda, or rho. Determinant is this product minus this, so it will be 2 minus rho square minus 1. And this is difference of the squares, so it will be 3 minus rho by 1 minus rho, 0. So we have two eigenvalues. Rho 1 is 1, rho 2 is 3, right? So we can find eigenvectors. So for eigenvectors, we now have to solve eigenvectors. We have to solve this problem. So we can solve still this, we will solve the problem in this form. So F minus rho E U is 0. So this matrix we already have here. So for rho equal 1, it's minus 1. So it will be 1, 1, 1, 1. U is 0, which means that you can find the first eigenvector is 1 minus 1. For rho 2 equal 3, so this matrix is minus 3, so it will be minus 1, 1, 1, minus 1, U is 0. So you find eigenvector is 1, 1. 1, 1, 0. So the general solution is the sum of the two solutions. So the xn is C1 coefficient multiplied the solution which corresponds to rho 1. So, but rho 1 in any power is 1, so it's just C1 U1. This is U1. Yeah, the next solution corresponds to the second eigenvalue, so it will be C2, 3 power k, and by the eigenvector. Or putting them together, so it will be C1 plus C2, 3 power k, C minus C1 plus C2, 3 power k. So this is a solution. And so this is k. And the initial condition we just compute k equals 0. So you put k equals 0, so it will be C1 plus C2, and minus C1 plus C2. So, of course, having any initial condition x0, you can choose C1, C2 to set it to from this equality, substitute, and you find it at any higher time. So, easy. So the example 2 is different. Save. So example 2. We take a matrix which will be 0, 1, minus 1, 0. Okay, so the characteristic equation, we should subtract rho from the diagonal. So it will be minus rho 1, minus 1, minus rho. So it will be rho square plus 1 equals 0, which means that the first eigenvalue is imaginary unit, and the second eigenvalue is conjugate to it, minus imaginary eigenvalue. So we only need to find eigenvector for the first, because for the second it will be complex conjugate. So we could have to put E. Put E here. Minus I1, minus 1, minus I. And then you find the eigenvector as, so what? 1i. Because when you multiply 1 and I, so it gives 0, and you can check that it's 0 for the second line. And automatically, rho 2 is conjugated to rho 1. Well, mathematician put a bar complex conjugate. Physicists put a star. I wonder what engineers put. Huh? Bar, no? Ah, good, so we're closer. Okay. So U2 is U1 bar. Mm-hmm. So general solution. So now we have to write a general solution. I will do it direct. Instead of using those formulas that I gave, I will do it direct. So I first write complex solution, then take real part, imaginary part. So this general complex solution will have the form xk of C1 by I power k 1i plus C2, and that will be complex conjugate. So minus I power k 1 minus I. And then you can take either you take real imaginary part, or you can make another trick. You can do something which will be directly equivalent. You take C1 and C2 complex conjugate as well, then the sum will be already real. So you take C1 to be A plus IB, and then we divide it by 2, it will be nicer. And C2 is A minus IB over 2. So if you substitute, it will be automatically real. So what is this? So this is, now remember that so how we will compute I power k. So what is the convenient way is you write it. This is exponent of I p over 2. This is I, no? And then you multiply by k, so you multiply by k. So the real part of it is cosine of this, and imaginary is a sign. So when you put then xk, when you sum up, so the a, it will be, I will skip this calculation, but it will be a do calculations. So at that moment, it's arithmetic. No, you substitute and cancel the terms. So what will remain is a 10 cosine kp k pi over 2. So coming from that expression, minus 0.1. I even don't need, no. Let's write it nicer. So there will be first xk is a by cosine pi over k over 2, which is I minus I1 or minus 1, depend on k. And then it will be minus sine pi over 2 plus b sine kp over 2 and plus cosine p over 2. So this is general solution explicitly. So we, given a matrix, we find explicitly the solution, which is real, and it corresponds, but despite the eigenvalues were complex. So the last example will show that it does not always work. And it will not work when the eigenvalues will not be distinct. So let's see the situation where they're not distinct, and we see that we cannot find the general solution. Actually, I didn't, okay. It's already done. So the third example is for the matrix F, which is 3, 1, minus 1, 1. Good. So okay. Let's make use of it. So it will be 3, 1, minus 1, 1. So we subtract rho from diagonal, so it will be 3 minus rho, 1 minus 1, 1 minus rho. So it's this product of these two, 3 minus rho by minus rho plus 1. And this is what? This is rho squared minus 4 rho, and then it will be 3 plus 1 plus 4 equals 0. And what you see that it has two roots, yeah, as we learned from school. So it's not one root, it's two roots, but there's the same. Right? So because this expression can be factorized as rho minus 2 square. So there are two roots. And there is, and now let's compute eigenvector. So you substitute 2, it will be 1 minus 1 minus 1. And you see that you can only make one eigenvector. You cannot take two eigenvectors. And the eigenvector will be 1 minus 1. So the solution that you can construct in the same way is uk equal 2 power k by this 1 minus 1. And multiply by arbitrary constant. So the initial condition that you can satisfy is, well, this will be 1, so it will be c minus c. So you cannot, not general. For example, if your initial condition is 1, 0, you cannot find a solution. So there is a problem. So this is a problem. And this problem we should leave for the next lecture. So the next lecture, I will show how to solve this equation in general. So I will remind you what is the Jordan normal form. This is not something extremely complicated, because I remember that mathematicians learn it in the very beginning and never remember what it is. So, so I will show you how to solve equation with the general form. So it will, next lecture it will become harder. Okay, the mathematics will become worse. We will solve a general. We will make a general solution, and then we will apply everything to the pendulum with a moving support and really determine the stability, instability, all these properties that we see, we saw in the videos. That will be next lecture, and after lunch, since we go to the labs, so I will show first experiments and the applications which are really very important, which actually changed the shape of the modern physics, and they are completely based on this theory. So it's not. There are fun applications, but there are tough applications. So, am I correct in time? No, so it's 2 hours. 2 hours, no, and then interval. Okay. So interval, please. Ah, tá. Tá bom, eu tenho que dizer isso. Obrigado. Mas meus vídeos estão lá, não aonde está. Acho que não vou precisar. Vou precisar no próximo aula. Não, mas esse não foi colocando aí porque tem alguns vídeos que são melhores. Também você vídeo você não colocou no site. Porque vídeo eu estou um pouco. Vídeo eu sou meio. Eu poder, estou colocando no site. Em princípio eu não acho que nenhum problema vai ter, mas em princípio deveria perguntar, não? So let's continue. So, the second lecture will be really mathematical. So I will first show how the general solution in all the possible cases is constructed for this discrete linear dynamical system, and then we go to the stability issues with definition theorems. So this will take somewhat 2/3 or hopefully less of this lecture, and then we start, and then we apply everything to the pendulum. Yeah, so this lecture is really heavily mathematical. Next lecture, we will gradually go from mathematics to applications and to experiments. So, the topic is multiple eigenvalues. Eigenvalues and Jordan chain. So what we discussed is that the eigenvalue problem, which gives you n eigenvalues, so this what's called characteristic equation, is a polynomial of degree n. So this is polynomial degree n polynomial. So there are guaranteed n roots. So the n roots are guaranteed, and not more. So it's exactly n complex root. But they can be the same. So when one of the root appears several times, it's what's called multiple eigenvalue. So the multiple eigenvalue rho, it's opposite to simple. No? So simple means that it appears only once in this list, and multiple appears several times. So if the eigenvalue is multiple, there are two multiplicities which are associated to this eigenvalue. So typically, so from linear algebra, you can associate two types of multiplicity. One multiplicity is very natural, which is algebraic. Algebraic multiplicity, and we call it MA, multiplicity algebraic, so it's bigger, or we call it than 1. Then when it counts how many roots, how many times this eigenvalue appears in this list of roots. No? So it's a multiplicity as a root. As a root of the characteristic equation. There is another multiplicity which we'll call geometric. Mg, it's also big or equal to 1, and it is equal. Now this multiplicity is linked to eigenvectors, because if you have a eigenvalue of which is multiple, so we know that if the eigenvalue is simple, a simple root, you can only get one eigenvector up to coefficient. So this is a rule. So you cannot be 2 or 3 and so on. So if it is simple, it's going to be only 1. But if it can be multiple, then in principle, for the same eigenvalue, you can find one or different linear independent solutions. So geometric multiplicity will count how many linear independent eigenvector you can get. So it's number of linearly independent eigenvectors. Well, there is a rule which we will see in a while. Why? So it tells no, both of them bigger than bigger or equal to than 1, but geometric multiplicity can not be larger. So the number of eigenvectors that you can get for the same eigenvalue is at most as many times you find it in the list of the roots. So you cannot get more eigenvectors. And the easiest case is a simple eigenvector, so the simple eigenvalue is when it appears once, so you see this is an agreement. So it's algebraic and geometric multiplicities, they are 1, so you can get one eigenvector for one eigenvalue. So it's just direct. But when multiplicity is bigger, for example, when the simplest case, when the multiplicity is 2, which means that you can have one eigenvector or you can have 2 eigenvectors. So, and this may have tremendous implications for the system because it is totally different behavior. Okay, so what to do? So if geometric multiplicity is smaller, strictly smaller than algebraic, it means that you cannot get as much eigenvector as the dimension of the space. So you cannot form bases in the space out of eigenvectors. So bases in the space cannot be formed using eigenvector. Which is bad because it's exactly what breaks our strategy to find solutions. Because for each eigenvalue we can find solution, but we cannot find as much as a dimension, so we cannot solve the problem in general. So what to do? And so we have to generalize eigenvalue problem. So the solution is construct so-called Jordan chain. So this is Jordan chain of vectors, so you can see it like a Jordan chain of equations, which starts with the eigenvalue problem. So if you have eigenvalue with some algebraic multiplicity, geometric multiplicity which is smaller, but it cannot be smaller than 1. You know, so one eigenvector you always have. So this is, we call it U1. So this is eigenvector. So we want to find F2. We cannot, for example, find in a situation when MA is 2, so there is 2 roots, but 1 eigenvector. No, we cannot find eigenvector which will, another eigenvector will satisfy the same rule. But in principle, what will be enough if the image of this vector by the dynamical system will at least be on a linear combination of U2 and U1. So it does not, U2 and U1 will still be invariant sets. So when you evolve U2 and 1, you still have a combination U2 and 1. So the way to write it is put plus U1. You can put any coefficient, but it will be the same, result will be the same. I mean, conceptually. So then this is called as associated or generalized eigenvector. But you can have situations which are much worse because, for example, algebraic multiplicity can be 5, geometric 1. So you have deficiency of, you need 4 extra vectors. So, which means that this procedure can be continued. Well, okay, let's write this. The next U3 will be rho U3, and then the remainder is a linear combination of U1, U2, but in principle you can show that you can just reduce it to this form. So you just plus U2, and that's, you can continue as much as you can. So as long as the solution exists, you're happy. So L, UL, U, L minus 1. And at certain moment you stop because you only stop at the moment when you cannot solve the next equation. So the solution does not exist, and then you stop. So this is a Jordan chain. This is called a Jordan chain, either Jordan chain of equations or Jordan chain of vectors, of the generalized eigenvectors. So now, let us write a very simple statement that we will show that now you having these vectors, you can also construct solution. So we'll, as a mathematician, I will write proposition. Then will be theorem. The proposition is that if U1, UL are those vectors, is the Jordan chain, for eigenvalue rho, then we can construct L solutions, L different solutions for the problem. So then, so xk, So first first solution we do have. So we already automatically have one solution because we have one eigenvector. So as we just did before. So it's rho k u1. So this is multiplier k times by the eigenvector. It's a solution, right? So this is what we did before. But next we can find another solution. You can do it exactly the same with the second vector, but this will not be a solution because every time you multiply by f, something with u1 appears. So there is additional part, so which is k rho k minus 1 u1. And then I will not write the next, but the last, I will write the last. So the last will be rho k ul. Then the next term will have the same form, k rho k minus 1 ul minus 1. And then blah, 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 blah. And then it will be k factorial l factorial k minus l factorial rho k minus l u1. Well, who remembers combinatoric can guess what is in between, but in principle you can write explicitly what the formula. So what important is these are all R solutions. Not only solutions are they're linearly independent. Linearly independent solutions for our system. So this is already good news because we have more solutions. So already more than just for each eigenvector. So let's make a very simple idea of the proof. So proof is just one by one. First, we already checked that it's solutions. Let's just check that the second is solution. So how we do it, you take f, apply it to the xk. What it will be rho k f u2 plus k rho k minus 1 f u1. But f u2 you take from the second equation, f u1 you take from the first in the Jordan chain. So this will be rho k. So f u2, remember this is written there. It's rho u2 plus rho 1 plus u1. And then it's plus k rho k minus 1 rho u1. Okay. And now this with this you combine, so it'll be rho k plus 1 u1. And then you combine these two, so it will be k plus 1 by rho k u2. And this is exactly the same thing, but in the next point. Right, so done. And you can do the same with all other equations. So essentially, this gives the idea. So you just substitute and use Jordan chain and see that actually this is why this combinatorial factor comes out, because of these manipulations. Okay, so the fact that they're linearly independent has to do with the initial conditions. So let's consider initial condition, which means k equals 0. When k equals 0, this set of solution just remove rho, right? And remove all these terms because k equals 0. So essentially at k equals 0, this solution is u1. In this case will be just u2 survives. And in the last solution will be ul. So essentially the fact that they're linearly independent is linked to the fact that the vectors in the Jordan chain are linearly independent, and we in a while will understand why. So you see that they satisfy very nice initial conditions. So we have more solutions. So let's, so the next step, let's see if this is enough to construct a general solution. So in order to do this, let's first rewrite this Jordan chain of equation in a matrix form. So what we do is I create a matrix, I compose a matrix by taking all vectors from a chain as columns. So this will be a matrix which is its horizontal dimension is n because each vector is dimension n, but vertical dimension is L because we just have L columns. So it's n by L matrix. So what I can do, I can write F multiplied by U. And on the right-hand side, you see that it's the same vectors with different prefactors. So you can write also in a matrix form. So the prefactors are organized by multiplying U from a right side. So if you, for example, in order to have row, you take a matrix with row here and zeros. Oh no, row and zeros here. Right? So you take this, the first column of this matrix will be FU1, and the first column of this matrix will be row by this column by U, which only gives you row U1, so it's the same. For the second equation, we have to put row for U2 and 1 for U1, so it will be row multiplies U2 and 1 multiplies U1, and 0, rest, and so on. So essentially it will be row on a diagonal. So let's not write zeros. So what not written is 0. And at the last equation, it will be like this. No? So we have a matrix which is called Jordan block. And it's L by L. Yeah, because you see, use n by L, so it's L by L. So it's Jordan block of size L. Okay. So now comes a very important result with the theorem about Jordan canonical form. The theorem about Jordan canonical form, which is probably the central, well, hardest part in the linear algebra course, which is we usually give for students. I will not prove it unless you ask. Okay, so what this theorem tells. Tell that for any matrix, F, you can construct, there exists non-singular matrix C, non-singular means you can invert it, such that you can conjugate. Conjugate means that you can multiply F by inverse matrix on the left and by the matrix on the right. This. And this will give us something very nice. This will give us the block diagonal matrix let's say till A. It will be block diagonal matrix, so 0, zeros, where all blocks G I are Jordan blocks. You see, so you can choose a matrix, multiply by it, or F by on the right, inverse on the left. So the something what you get has a very nice structure. It has everywhere zeros, only there are eigenvalues on diagonal, and they are eigenvalues, you know, because it's always zero. It's diagonal. It's upper triangular matrix, and there's some of the ones appear here, one, and the rest is zero. The good part is that you can multiply. You can put C on the other side. So let's call this all J. So the good part is that what you can do. We don't need this anymore. Split. So what you can do is you multiply by C on the right, so C you move on the other side, so the equation will be written as FC equals CJ. So now what we can do, we can take matrix C, which is n by n, and cut it in a form which follows exactly the same structure of the Jordan form. So it will be, well, in order to not confuse, I will put indices with letters. So it's UA, UB. So let's write it UA, UB also here. A, B, etc. No? And now each block, like you take UA, it gives you first if this block has a size, let's say L, it will give first vertical lines of this product, but first vertical lines, L vertical lines of this product are given by this Jordan substructure, so it will be same UA by GA. So you come back to exactly the equation that we had. So in other words, the Jordan canonical form tells you that you can, this matrix, its columns is exactly the vectors of the Jordan chain. And the Jordan theorem tells that you can make a basis because C is non-singular. So you can fill the basis in the space just by these generalized eigenvectors. So the corollary is, I will not put details, but corollary is that the general solution is a linear combination of solutions. Let's call them star. So these all solutions, we say the star. For all Jordan blocks So the procedure is the following. you get a matrix. Then you compute the Jordan form, which is when matrix compute non-trivial Jordan form. It's by itself quite a complicated numerical problem, but it's not your business. So there is even software. So you compute its Jordan form. The Jordan form gives you eigenvalues and eigenvectors, which are columns of this matrix C. And for each block, you say that this is U1, U2, U3 until UL. So you take solutions from this system and you sum them with arbitrary coefficients. It gives you a solution. So let's make an example. Example, we do an example here. So I keep this system. Example 4, which will be follow-up of example 3. So example 3 was what? It was matrix was F was 3, 1, minus 1, so 3, 1, minus 1, 1. Remember that we computed that there are two eigenvalues were equal. So the algebraic multiplicity is 2. So the algebraic multiplicity is a number of eigenvalues. So we also found that there is only one eigenvector, because if you write this, so if you write this system for the eigenvector, or you can write it in the equivalent form, so you take it on the left, put it on the left. It's minus rho E U1. And so what it is, when you subtract 2 from diagonal, it is 1, so 3 minus 2, 1 minus 1 minus 1, U1 equals 0, and we already found that U1 is 1 minus 1. Yeah, so there's just one eigenvector. So we conclude that geometric multiplicity is 1. Good. So there will be one more. So we have to find the next. So we have to find a generalized eigenvector which must solve this problem. The Jordan theorem ensures that there will be one. So how we do, we again put this rho u on the left, so to make it simpler. So this is the same matrix. So this is the same matrix. So it's 1, 1, minus 1, minus 1, u2. And it should be equal to u1, not to 0. So it should be equal to 1 minus 1. Solution is not unique, but does matter. You just take the one you like more. Which I like more. I like more 1, 0. So u2 is 1, 0 solves this equation. And in principle, you can check if you can continue. Already by the Jordan theorem, you kind of guess you cannot, because otherwise you would have one more vector. But we can check. So the next equation will be for u3, and should be equal to u2. So this equation has the same form, so it will be 1 minus 1, 1 minus 1, by U3, and it should be equal to U2. 1, 0, and I think it is quite obvious that it's never satisfied, right? Because whatever linear combination of 1 minus 1, it will be A minus A, so it cannot be 1, 0. So Jordan block, it's over. And then we take two solutions. So we have two vectors. One vector is U2, another vector is U1. And you can construct general solution out of this chain. And we will only use first is the second, yeah, because we only have two vectors. So we can take the first, which is, let's just write them explicitly. So C1 rho k U1, this will be the first. We multiply with arbitrary coefficient. And then C2 by the second, which will be this rho k U2 plus k rho k minus 1 U1. Okay, and now you just substitute everything, so it will be C1 2 k 1 minus 1 plus C2, and then it will be rho k 2 power k 1 0 here plus k 2 k minus 1 minus 1. Well, you can collect it to the same one single vector, but clearly we have explicitly know all subsequent solutions, and in order to see that it works, we have to find initial condition. So let's see what is initial condition. So k x0 is what? So you remove this 2 power k, they become 1, and this term becomes 0. So what is remained is C1 minus C1, and here will be C2. So it's clear that for any initial condition, you can choose C1, C2 to satisfy it, and then you subset this C1, C2, and you have solution for any time. So really, we do have solutions for all the times. And this is how it's constructed. So it's always can be constructed. So the only observation which we say, which we can also have, which we can link the multiplicity to the Jordan form. So the geometric multiplicity is the amount of linearly independent eigenvectors. So each Jordan block has one eigenvector only. So the geometric multiplicity is how many Jordan blocks for this eigenvalue appears in the canonical form. So this is number of the Jordan blocks. But algebraic multiplicity is counting eigenvalues. So each Jordan block has as much eigenvalue as its size. So the algebraic multiplicity is the sum of the sizes of the corresponding Jordan blocks. Okay. So we finished with linear algebra. And go to the stability theory. Okay, now what do we have? We know, no, yes. So now we solve the equation. And we want to know what is the influence of how from knowing this solution we can make any conclusion from the properties of the system. You know? So let's, we went sufficiently deep in the mathematics, so we found solution, so what does it mean for the system? And first, we will not say what does it mean for the pendulum and so on. Let's first respond what does it mean for the differential, for the equation, for differential equation. So in order to formalize, we will give some definitions. Stability. Stability theory. Okay, so remember that we had our equation for the continuous time, which had this form, and we had the equilibrium solution. Y star equilibrium means that it doesn't depend on time. So this is a solution. So assume that this is the solution of your pendulum. So the equilibrium solution of the, there are two equilibrium solutions of the pendulum. Looking up, down, looking up. Right? So we want to say if this solution is stable or not. So first definition of the Lyapunov stability. So the definition of stability is the following. I will try to change. This pen, they have to rest. Then they keep it calm. We don't need, no, but so the equilibrium Y star is stable. It's called stable. Called so now now I start this epsilon delta. So this, I think this epsilon delta should frighten engineers to them. So this is my goal. so it's called stable. It's called stable if for any positive epsilon, there exists positive delta such that the solution remains epsilon close to the equilibrium for all times, for all positive times, if initial condition was delta close. So let's see what does it mean. So what does it mean is the following. So let's assume that we have just one y, you know? So y was real, just to make it easy. And put time. Well, if so you have many more y, so there is y2, y3, y4. So we have an equilibrium solution, which is does not depend on time. So this is y star. So the definition asks for two different quantities. One quantity is epsilon, and epsilon is any. And epsilon want to control our solution forever. So we will put, so we say that for any epsilon, any actually means any small. No? So you can put as small window as you want near y. So this is epsilon size, plus minus epsilon. And we want that our solution never exits this region. And so the system is stable if you can guarantee this property by taking solution initial condition sufficiently close to the equilibrium. So you put another threshold. So you put another threshold, which is delta. This is delta, but it only works for initial condition. So which means that whenever, so for any epsilon, whenever small you want to take, you can take smaller neighborhood. So any solution which comes out will not escape. So you control, so you can control your solution to be epsilon close to the equilibrium, whatever small epsilon is, by forever, this is important, forever, by taking the initial condition delta close to the equilibrium. So if you guarantee that you started sufficiently close to equilibrium, you know that you'll be guaranteed as close to equilibrium as you want forever. Okay. So the small variation of this of the definition is the equilibrium is called asymptotically stable. Stable if then all the same text, and additionally the limit as time goes to plus infinity, the solution should approach y star. So the solution is called asymptotically stable if for large times it not only will, it can oscillate, but at very large times it should relax exactly at y star. So then it's asymptotically stable. Asymptotic stability is a bit, is a very good notion because this is what we can usually prove. The proving stability, well, actually there's big problems because, well, so the asymptotic stability is usually easier to prove. Stability is usually stability which is not asymptotic is harder to prove, but reality is that all conservative systems they cannot be stable. So this is well, this is why we have job. So okay, and we can write a counterpart of this definition. So this will be definition 1, so it will be definition 2. We can write the same, but for discrete system, yeah? Because we had we also had discrete system, which was x k plus 1. No, y. Let's we're in y plus 1 equal f Poincare map of yk. Yeah? So there is, remember, this is photographing at each period. And we also had a fixed point because y star is not moved by this Poincare map. So we can say that y star is stable for the system if, so now I will, so you probably put mathematical symbols, is for any epsilon positive, there exists delta positive such that the solution is controlled at all times, so in the epsilon neighborhood for all, but now time is discrete, and the initial condition, which is delta controlled. Exactly the same notion by you substitute continuous time by discrete time, and discrete time dynamics by continuous dynamics by discrete dynamics. So it's essentially the same. Probably the graphical explanation will be slightly different. So let's take. This was only one variable. So let's see how it works with two variables. So we take y1, y2, and this is our y star. So our equilibrium. So what we say is that so y star is red, no? It must be red. So we say that you can define for any epsilon neighborhood, any epsilon ball around this y star, if you start delta close, you can find delta smaller. So if you start delta close, so if you put initial condition somewhere inside, so this is y0, then the map will jump to different points, but will never get out from the ball. So you can jump, you never get out of the ball. And of course, there is a counterpart for asymptotic stability, asymptotically stable, if all the same is true, and additionally, it jumps, but finally it jumps closer, and still rests. So next is a theorem. No, several theorems. The first is something easy, so let's make it even in a simple form. No. First theorem is the following. So first is this is important. Let's call it proposition. It's easy. So the y star is asymptotically or just stable for continuous time system is equivalent to say that y star is asymptotically or just stable for discrete time system. So in the sense that if we just want to know stability, we can work with the Poincare map. So this is huge simplification. So we don't need to solve ordinary differential equation. We just use map. The reason why it's true comes to the just simply continuous dependence of solution on initial conditions. So it essentially means that it's enough to see on photographs after each period, because between periods nothing special can happen. Because period is finite, it's always the same. So So it means that from our pendulum, which was a more general system, we will only focus on the Poincare map. The next proposition, well, actually it's so from now on we only concentrate or for the next series we'll only concentrate on the discrete time system of Poincare map because it automatically gives the result for this continuous time system. So the first is let's first it will be Floquet's theorem, but I will first put it in a simpler form. So let all so exactly the same definition you can say, or you can write for linearized system, right? Linearized system. So linearized system on the left-hand side, it's x dot equal gtx, and on the right-hand side, which is discrete time, it was this. It's also continuous time system, discrete time system. So we can say this table and this table, and they both has equilibrium at 0. So you can say that whether 0 is in equilibrium, if it's stable, asymptotically stable, just the same formula. And here, if it's 0 is stable, asymptotically stable, of course, we have this relation. So first, let us see when this system is stable. So when the 0 is stable for this system. So the simple case is when all eigenvalues are different, are simple. So remember this, we had rho n eigenvalues, which are all simple. And which means that we have general solution. That means that xk you can write as a solution over summing over all modes with arbitrary coefficients, and it will be rho jk uj. So the equilibrium x is 0 is stable, is asymptotically stable. Is stable. If so, you see what you need. You need for asymptotic stability. You need that this will not grow, right? And this is a sum of independent terms. So essentially, you need that each term does not grow. And the only way where the time enters in the power, so the condition for this term does not grow is that this rho is in absolute value smaller than 1, yeah, or equal. If and only if, well, I will teach you mathematics. So if and only if is if, okay? So it's if and only if. Is stable if and only if, in this case, all absolute values of the eigenvalues are smaller or equal to 1, which simply means that absolute value of each term it does not change in time. And clearly it is asymptotically stable if this is smaller than 1. Because if it's smaller than 1, if it's equal to 1, then it will not go to the 0. Yeah, so in order to, but we need, for the asymptotic stability, we need that at large k it should be 0. So we need rho have absolute value smaller than 1 for if all, again, all. So there is a very nice graphical representation of it. So of course, somehow remember that rho are complex. But if rho are real, this is exactly like this. If rho complex, you have to put real imaginary part of it. But I'm trying to skip this. It's just detail because essentially the result is the same. So instead of rho k, you take modulus, rho k cosine and sine. So I already wrote these solutions. So if you plot imaginary in the complex plane for the rho, there is this magic unit circle. So if you're inside, you're good. So if you're inside, you're good. You're asymptotically stable. So all eigenvalues means this, you are asymptotically stable. If you want to be stable, you can allow to be on a unit circle as well. Okay. But as soon as you go out, at least one of the eigenvalues go out, it's instability, unstable. At least one. So one is enough. So in the case, there is a Floquet theorem, so let's write it down. So the Floquet theorem by the Floquet, it tells that solution in general. So this is a specific case when all rho are different, and we know that in principle all rho do not have to be equal. There can be multiplicity, geometric, algebraic, and all these Jordan blocks and so on. So the Floquet said that the x0 is stable for this linear system. So is a stable equilibrium for this system if and only if all eigenvalues are inside in or on a unitary circle, but now so now what? Now you have this. Remember that the solution that we had had this form. So now the solution, in a general solution, had this form of the Jordan chain. So the second solution was like xk was this, just remember what was the second solution. It was rho k u1 plus k rho k minus 1 u2, etc. So you see, if rho is smaller than 1 in absolute value, this goes down. And this goes down because despite k grows, but it grows linearly, and this goes to 0 exponentially. So when rho has absolute value smaller than 1, it always wins. But if it has absolute value equal 1, it doesn't matter. So the k wins. So it diverges, which means that if and for all eigenvalues which are exactly on a unit circle, we cannot have these kind of solutions because otherwise it will be unstable. So for all eigenvalues which are on a unit circle, and remember when they have these solutions appear every time when we have a Jordan block, which means at least size 2 or 3. So we cannot have any Jordan block of size 2. And this is the case when the algebraic and geometric multiplicities are the same. So it's called semi-simple eigenvalue. So that means that there are as many Jordan blocks as roots, so which means that it's actually diagonal. There is no ones. Ones do not appear. So it's a just simple generalization. And for asymptotically stable, nothing changes. So in a general form, there is only, you have to be careful with the eigenvalues which are on the unit circle. Some of them give you stable situations, some of them give you unstable. You should be careful despite it doesn't matter for the next reason. So what the reason is the following. So there is a very, very important issue is that linearized system is not the original system, which people often forget. The linearized system was obtained from the, so we started with a Poincare map, which is exact. And what we did, we expanded F in Taylor series and neglected higher order term. And it gave us linearized system. And this is approximate, because we neglected this. We neglected this term. So they're not the same. So they're very close to each other because we neglected very small term. But remember that definition of Lyapunov stability tells that the solution do not depart for all times. So despite that you have very small term, but if you wait long enough, something very small, if you wait long enough, become big. Yeah, so this happens sometimes. So in principle, if we know everything about stability of the system, it does not guarantee that this is stable. Yeah. So the next theorem exactly tells when knowing properties of this system, we can know the properties of the original system, which is exactly what our final goal. So we want to find stability of the equilibrium of the pendulum. It's non-linear system. We linearized, found Fouquet metrics, found eigenvalues, checked if it's stable. But does it imply that the original is stable or not? So this gives final theorem. It's by Lyapunov. And it has two cases. So Y star is the equilibrium of nonlinear system. So let's say, for example, doesn't matter if it's this or it's this, because it's from point of view of stability is the same. So there are two situations. So if all eigenvalues has a absolute value smaller than 1, so all of them are inside. So you see, by the Fouquet theorem, the linearized system is asymptotically stable. So Lyapunov tells that in this case, you guarantee that Y star is asymptotically stable. So this is very good news. So if you linearize system is asymptotically stable, this term does not matter at large time. So whatever you neglected, it will never accumulate to something large. So it's also asymptotically stable. And another case is if you have eigenvalue which is outside unit circle, at least if there exists at least one eigenvalue with absolute value bigger than 1, we know that by Floquet, linearized system is unstable. So Lyapunov also guarantees that it's unstable here. But you see, it does not cover all cases. Yeah, so there is a case which is special case. Case of Lyapunov. So there is only case which does not enter to this 2 is when all eigenvalues has absolute value small or equal to 1 and some are exactly on a unit circle. So that is neither one nor the other. And in this case, it's a problem. It's a problem because you cannot, in this case, it's not a problem because linear stability. Why it's a problem? Because it's linear stability, which is a Floquet theorem, have no correspondence to nonlinear stability. What does it mean is, it means that even despite Floquet theorem tells you you are stable for linearized problem, you can arrange nonlinear terms which will make it unstable, and if it is unstable, it makes it stable. So essentially these peculiarities with Jordan normal form is actually do not matter that much from this point of view. And luckily, many physical systems fall to the special case. So we cannot solve it by the Lyapunov theorem. Though many cases are. So there is these two things. Okay, so I finished this general theory, and you see that there was a question. You see all the theory I gave for general systems. So the dimension of the vector y is n. So it's all this works not only for pendulum, which is 1 degree of freedom, but for n degree of freedom system. And this is a kind of machine to study stability. You take a system, put it in the normal form, linearize, solve over period, find Floquet metrics, find eigenvalues, check stability, and then you apply the theorems. And then you know it's stable or not. So we move to, so we move to the next question, but he said I would prefer to do an interval. So questions. So now, tell who understood it very well. Well, good. So then that means that I will, let's take a rest. Oh, good. No. It's not about equivalence. It's just about stability. So it does not show equivalence of the vector fields of the local. No. It is a much more rough property. Yeah. So it's much less informative than Kaufman-Grobman. At one side and another side, on another side, it just tells you are you far off or not. It doesn't tell you how you are organized. Yeah. no, it's just far or not. And especially it works only in this hyperbolic situation. So it's only, well, as well as Hartmann-Grove. Okay, so let's make a. I will wait. I will put some. So let's. Let's put. Make a 5 minutes break just to relax, and then we go to the next part. And I will clean the board. triggers analog to the changing vertically and the support point, so the classical situation that we'll also consider soon is when we go up and down, let's harmonic, it's a cosine, up and down, but I think that only very trained people can sit and stand up in cosine. theory, my time changes by 2 pi, and for some simple reason that because our solution will be cosine phi. Just to which is called basic calculation. No, no, it's not basic. Basic calculation is linear. So it's not yet basic calculation. let's write how to do it. Because x, so we already have this relation, but additionally we have the relation that at x at 5 is related to x at 0 to the first matrix, and x of 2 pi is related by the second matrix to x at 5, but then we substitute it inside, we become f1, f2, f1, f0. So simply if we find both these matrices, So x at 0, let's compute it at 0. You put time 0, so what happens? Cosine become 1, this become 1, this become 0, 0, 0, 1. It's identity matrix, so A1 is remains. So x at 0 is A1 is 2. And x at pi Okay, let's start. So, just there was really some, let's call it misprint in lecture notes. So the H double dot is not delta and minus delta. What was supposed to be the delta is amplitude of the vibrations of the support. And then the second derivative, it should be omega square in front. So that's how the delta become a parameter which defines amplitude. And then when you make it change of the time variable, you really get 1 and minus 1 here, and there is no omega square here. Yeah, so it's just to make. Okay, so let's continue. Because this is important moment that we will use in a while. It will be important for the stabilization. So we have this. We found explicitly the Floquet matrix for the system. So in the general theory, I thought that usually this is impossible, but it's really not a big problem because Floquet matrix can be found numerically, rather in a rather straightforward way. So it's not a problem. But anyway, well, it's not a problem unless if the number of degrees of freedom is large, but reasonably. When it becomes million, then it's become a problem. Because you need to, so if n is the number of your phase variables, you need to solve n square ordinary differential equations. Okay, but in this case, we found Floquet matrix explicitly. It's a product of these two matrices. And it's actually even easier. We have a product of two eigenvalues give 1. And if the product of two eigenvalues give 1, there are 3 cases when this can happen. Because remember, they're complex, no? The one case, if they're both real. They're both real. And different. And distinct. So in this case, well, not in this case, in all the cases, if you have one eigenvalue ρ1, the another is inverse. And the way how to figure out the situation is that you can check that the trace of the matrix of the Floquet matrix. See the trace of the Floquet matrix, trace of any matrix. Trace of any matrix. Trace is the sum of diagonal elements. And sum of diagonal elements is always the sum of all eigenvalues. So this is from linear algebra. So if the trace of the, if the ρ1 and ρ2 are two real values, and it's not 1 or minus 1, so they're different. So then what you can check, so if ρ1 is different from ρ2, both real, and ρ2 is 1 over 1, check that sum, which is bigger than 2, always. Well, this is not difficult. You put multiply by ρ1, become 2 ρ1, so ρ square, you put it here, become full square, right? So I will not do it. So in this case is directly determined by this condition. So case R corresponds when both are real and distinct, it corresponds to trace bigger than 2. The another case is when they're different and complex. When they're different and complex, you see the problem is that they also not only rho 2 equal 1 over rho 1, but if they're complex, they're also complex conjugated. Right? They're also complex conjugated. And which means that they have the same absolute value. So it's only possible if the absolute value is 1. So in this case, what really happens is that rho 1 is some complex eigenvalue with unitary absolute value. So the absolute value is 1, and rho 2 is complex conjugated. No? So phi is not 0, not pi, so they're complex. So in this case, you see, so in this case, so let's make it. So in the first case, so this is imaginary part of rho, real part of rho. So in the first case, we had either this situation, rho 1, rho 2, or they can be on the other side. So in this case A. Case B is case B is okay, this is case A. Let's forget about it. So this is case A. In case B, they're here. So they're complex conjugate. So the sum, if you take a sum of the two, imaginary part cancels and real part is smaller than 1. So the sum of the eigenvalues is smaller than 2. So this case is defined by the trace of f is smaller than 2. And there is an intermediate case C when the trace is just exactly 2, and it corresponds to the case when the rho 1 is and rho 2 are equal. And when they're equal, it's only possible when it's plus 1 and minus 1. So equal 1 or minus 1, and this is case when the trace of matrix is 2. So now what we immediately can conclude is that, I'll erase it. So we have three situations. Either they're real, or they're complex conjugated, or they're at 1 and plus or minus 1. Certainly, this situation is unstable, because one of the eigenvalues is outside unit circle. So which say that if trace of the model. So if the trace is, so this case is case A, so the trace should be bigger than 2. So the trace bigger than 2 is instability. For the linear system, the trace smaller than 2 correspond to the two complex conjugated eigenvalues, which are exactly on a unit circle, and they're simple. So this is stable situation. And since usually if you want to know what is stable, what is unstable, you need a boundary. So we have a very simple criterion which determines the boundary. So the trace is exactly 2, it is a stability boundary. So essentially, you need to compute trace and then apply this criterion. So the trace of the matrix F. So now you have to really compute. So you need to multiply these two matrices. You get the matrix F and you sum diagonal elements. So you don't need to compute all 4 elements. You just need to compute diagonal elements. And I will not, I already did it here. So you multiply the matrices and take sum of diagonal elements. So I think we can skip this computation. So the trace will be 2 times cosine omega 1 pi, cosine omega 2 pi. So why? Because see, you multiply f2 by f1, and the first element will be cosine by cosine, sine by sine. But sine by sine, you see it, so it's like this, poof. So it will be omega 2 over omega 1. So there will be another term which contains fractions. Omega 1 over omega 2 plus omega 2 over omega 1 sine omega 1 pi sine omega 2 pi. So all we need, so we have a formula. So if you need to find stability diagram, just find where it's 2. Yeah, you will have some regions which are splitted by this boundary, and then check in which region is positive or bigger than 2, in which is negative, smaller than 2, and you find where it's stable, where it's unstable. So let's just do it. Well, certainly we can not do it explicitly, but let's first gain some intuition, and then we'll see what it is exactly. Okay. So our criterion is that this should be equal to. So let's find where this is equal to. Okay, so what? So we have 2 coefficients, A and B, in our problem. And remember, these are 2 parameters, which were computed through the, so they're here. So there is A, which is essentially responsible for gravity, and B responsible for the oscillations. And remember that we had omega 1, it was square root of A plus B, and omega 2 was square root of A minus B. So first, let's take B equals 0. B equals 0 means no static support. So this is usual pendulum. We don't anymore move the support. So it's usual pendulum. So in this case, omega 1 is square root of A. Omega 2 is the square root of A. And then this expression becomes trace of F. So this becomes 2. This is 2. So we have a 2. So we will have 2. I will take it out. So it will be cosine omega 1, which is square root of A pi. So it's cosine square root of A pi by the same cosine here. So cosine square. And this will be 2, which I put out already, and it will be sine squared with minus. So this is important. This is cosine of the double angle, so it's 2 cosine 2 square root of A pi. So this is, and we have to compute it where it's equal to 2. So it's, first of all, it's equal to 2 only when this is not K, what I used. N, which is when this quantity is so it should be 1 or minus 1. Yeah? So it's n times pi. In integer number of pi's, right? So then it's 1 and it's 2. And otherwise it's smaller than 2. So which means that the 2 square root of a pi equal n pi. Pi cancels, and we get that a is n squared over 4, where n is 1, 2, etc. So we have some specific values of a where something interesting happens. So these are resonant points. Okay? And for other values of a, what do we have? We have the trace of f will be smaller than 2, which by this condition is stability. Good. So let's draw the picture. So this will be a parameter. This will be b. So you see a is proportional to j, to g, the gravity, and b is proportional to the amplitude of the excitation. So we have interesting points are when n is 1, it will be 1 over 4. When n is 2, it will be 1. The next point will be n is 3, it's 9 over 3 over 4, etc. So I will only draw b positive because b negative is exactly the same. No, there is symmetry. So if you put, cannot be different if you amplitude is delta or minus delta. So you can also see actually b is positive and in negative it switches omega 1 and omega 2, but they come symmetrically. So there will be no difference. So I'll only plot b positive. So we have interesting points. So here it's stable. Here it's stable. So which means that in principle you can have something unstable only near those points. Something if unstable it should be because the instability, any instability region of instability will be bounded by the curve of trace equal to, but trace equal to only here, and here. So if there are some regions, they will come up near those points. And now let's just first check. Let's first check that really there is instability nearby. So what we do? Well, before we do it, let's just check directly. So let's consider small b, and we just make it. So let's take b as epsilon. No. Consider small what? Oh, okay. So consider parameters. as an example, A near this point, 1/4, and we add something small. And I add some epsilon over square over pi square. It's just because I want to do some nice computation. So, and then B we will take as epsilon over pi. So we consider the A and B along some curve. So this is parameterized by epsilon. Okay, and consider and assume that epsilon is small. So this is a system where we have a small excitation already. And now check what is a trace. So omega 1. So first compute omega 1, omega 2. Omega 1 is square root of why I did it. Exact. It's exact. So yeah, this was the reason. So the reason was that to have exact computation. So A plus B, no? A plus B, and this plus this. It's square root of 1/4 plus epsilon over pi plus epsilon pi over pi squared, 1/2. And this is a full square. This was the reason. So it's 1/2 plus epsilon over pi. So take a square of this and you have this. And in the omega 2, it is A minus B, and for the same reason it will be 1/2 minus epsilon over pi. Okay? So then we can compute trace by this formula exactly. So the trace of the matrix of the Floquet matrix, it will be so you see we have to put omega 1 and omega 2, and it will be okay, let's write it down. It will be 2 cosine this omega 1 pi. So it will be pi over 2 plus epsilon cosine pi over 2 minus epsilon. And then there is a plus this ratio minus. So it is this divided by this, so there will be let's write it as it was. Omega 1 over omega 2 plus omega 2 over omega 1, and then it will be sine by sine. So it will be sine pi over 2 plus epsilon and sine pi over 2 minus epsilon. So here, one is sine, another minus. One is sine of epsilon. This is sine of epsilon. This is minus sine of epsilon. Right? Because when you add pi over 2, it becomes sine. It will be minus 2 sine square epsilon. So this is first term. And this term, well, substitute this expression, this, and just make one fraction. This is easy computation, but I will skip it. So it will be 1/4. So because you have to put here, and then this expression here, and sum up the fraction. So this is, I will skip. So it will be this. And again, this is cosine epsilon and cosine epsilon. So this is, for epsilon small, this is negative, always. Oh, no, what I'm telling. So this is, you see, this is bigger than 1. Yeah, this whole term is bigger than 1 because for small, here you add and here you subtract. So if, and cosine square is positive, so you can write this coefficient, it's 1 plus something. And when you put 1, cosine square sums up with sine square, it will give you 2 minus 2 and minus something. So it's less than minus 2. See, because since this coefficient bigger than 1, sine square plus cosine square will give minus 2, and there will be something negative on top of it. Okay, so it's smaller than minus 2, which, if you take an absolute value, is bigger than 2, because negative, which is, by this classification, instability. It's unstable. So at least you know that if you start shake your pendulum with the parameters along this curve, your lower position will be unstable. So you will start to swing. So at least you guarantee it. Well, of course, you can go on and make more and more analysis by hand, but it's actually not so necessary because we have a formula where you can just substitute and plot on a plane stability and instability diagrams on a computer. So these are this is so first of all, this is what happens. So there is a region of instability, which is kind of rather wide. At 1, there is also a region of instability, which is much thinner. Then there is a region at 9/4, slightly begins slightly thicker, and so on. So at each this resonance point really are adjusted to some instability region. And you can do more, so you can do more. So if you compute for larger and larger values of V, so we have these regions, but they starting to be bigger and bigger. So this is exactly diagram of stability for the Meissner equation. So what is crossed is the stability, white is where it's unstable. So this is completely in agreement. So what we can say about this? What we can say is we still can give something interesting before we before we come into physics, we can give something interesting mathematically. So what are the eigenvalues? What are the eigenvalues? So if you check the trace, so the trace of f, remember, so exactly at the resonance point, so at b equals 0 and a equal n square, over 4, the trace of f, remember, trace of f is this expression without modulus. It will be 2 cosine n pi. So 2 minus 1 n. So it will be 2 minus 1 n. So it's changing. It's minus 1 plus 1, minus 2 plus 2, minus plus 2 plus 2. So when it's, so which means that rho, the eigenvalues which are exactly at this point, they are minus 1 when n is odd, and 1 when n is even. So at this point we have eigenvalues to be minus 1, and this point we have eigenvalue to be 1, and this point again eigenvalues are minus 1, and so on. So they alternate. Minus 1, 1, minus 1. This is nice. Why? Because now we can understand how the eigenvalues change. This can be removed completely. So what I will do, I will take a straight line. Plot a straight line horizontally. So what does this straight line mean? This straight line means that I fix B, so I fix the amplitude of your pendulum, but I start, as I go to larger A, remember that A was G L omega square. So what happens is that I decrease, larger L means smaller frequency. So I make, here the frequency is very strong, here its frequency is smaller, and here's smaller and smaller. So I will decrease the frequency, keeping the amplitude the same. So what happens with eigenvalues? So we'll make a big picture. The real part of eigenvalue, imaginary part of eigenvalue, and then we have the circle. This unitary circle. So we, at this point, so let's start at a certain point. So we start here, this point 1. At the point, let's call it A. So at point A, two eigenvalues are minus 1. So because the boundary always correspond to the, remember, by our classification, boundary always to correspond to double eigenvalue, and it's either 1 or minus 1. So since it's minus 1 here, so it's minus 1 here. So at the point A, the two eigenvalues are here. just before A, it was stable. Stable means that eigenvalues are on a unit circle. So which means that at larger frequencies they were here, and then I decreased frequencies, they came and made it -1. Then you enter the instability region. So they should get out from a unit circle, which is only possible in this direction. They split to become real, but this is not forever. They come back to the unit circle, and again they are -1 because at that point it was -1, just by continuity. So they just turn and return. And then what happens? Then it's stable, and we continue in the stability region until we hit another instability zone, but hits 1. So what they do, they have to to travel the full imaginary circle, or full the unit circle to come and meet at 1. Again, you enter the instability region and exit through 1. So again, they do the same. They exit, they become unstable, and then they enter back. So the system becomes stable, and then as you increase A or decrease frequency more, you again enter to instability range, but at -1. So they have to make it all the way back to -1. Oops. And then make the same dance here, then come back. So this is what they do as you decrease frequency. So this is a picture. What is the implication of this picture? The first implication is that is about geometry. So you can see that each boundary of the instability corresponds to double eigenvalue, which is either 1 or -1. So here it's 1, here it's -1. And there are only 2 eigenvalues. So it cannot be at the same point 1, both to be 1 at the same point where they both is -1. So these boundaries cannot cross. And this boundary, because it's -1 and 1 and -1, this boundary cannot cross, this boundary cannot cross, and so on. So no boundaries of different regions can cross. So you can see that the boundary, they come very, very close to each other, but they never cross. At the same time, the boundary from the same region, they correspond to the same eigenvalue, so they can cross, and this is what happens. So every boundary crosses several times as you increase the amplitude. So this is a very nice geometry of this. Okay, so this is good. So this is about Mathieu equation, and again, still, let's wait a little bit to come before we go to physics. So let's study very briefly another equation, which is more famous than Meissner, which is the Mathieu equation. So the Mathieu equation is almost like Meissner. The Meissner, good part of Meissner equation is that we can solve it by hand. So the Mathieu equation you cannot solve by hand, and it corresponds to a different situation. So it corresponds to a situation which is where the position of the pendulum, the vertical position of the pendulum, is sinusoidal. So it's not going with fixed acceleration, fixed acceleration, but it's just go up and down as a cosine. So doing the same manipulations, remember we had to define new time. We get to the equation which is exactly the same as Meissner. Only here it's not a function which is 1 minus 1, but cosine. So this is the main difference. And this is what's called Mathieu equation. So this is a very famous Mathieu equation, and I guess it was not. What I remember, it was not motivated by pendulum. It was coming from also wave dynamics. Okay, so for Mathieu equation, you can do exactly the same analysis. And what you will find is that at least resonance point will be exactly the same position, because resonance points correspond to zero of the amplitude of perturbation. So the resonance point will be exactly the same point, but the zones will be different. And these zones you can only compute numerically. Well, of course, you can do analysis, but at the end, if you want to know where they are, you have to go to numerics. And this is how it looks like. So there is a zone which appears at 1/2. There is a zone appears at 1, at 9/4, at 4, and so on. And each one is thinner. Well, the property, for some reason, they don't self-intersect. And we know that they cannot intersect between them. So there is no intersection at all. Okay, so this is the result. So now let's see what does it mean. What does it mean for our pendulum? Before, what does it mean? I should ask a question. So we found this stability diagram for the Mathieu equation. So what does it mean for the pendulum? Does it mean that stable where it's white and unstable where it's gray? So remember that we had a, so why I'm asking this question first of all? Because this is the stability diagram of the linearized system. And I told you that the original system non-linear. So there is not direct automatic correspondence between the two. So there is Lyapunov theorem. We tell that except for the special Lyapunov cases, it's direct, but not always. So what we can say that in the gray region, when it is unstable, the two eigenvalues are here. So one of them is outside. So it means that in the gray region, it's also unstable for the original pendulum. But in the white region, they are exactly on a unit circle. So this is a special case of Lyapunov. So white region, in fact, does not guarantee that we are stable. So what is sure is that in the gray region we're unstable, but for white region that we're stable, we're not guaranteed. And it's actually true that we're stable, but the proof is already much more complicated. But there is one trick which can make it simpler. So it's a kind of physically motivated trick. And this trick is the following. So any pendulum that we have has a friction. So let's put friction. So we consider equation with damping. So the damping term is modeled as a first derivative with respect to phi. So essentially you just add the small term, we think it's small. So this will be damping. Which always exists. So let's start study stability of this system. So what happens is when you add this term with delta, the eigenvalues which we will not make it, the analysis is the same, right? You create 4K matrix, compute and so on, because this will still be 2 by 2, and analysis will be the same, just will be one more term in the Fourier matrix, in the G matrix. So idea of the analysis is the same. You compute eigenvalues, check where they are. So it turns out that as delta is positive, the eigenvalues which were on a unit circle, they move inside. And as they move inside, the system becomes asymptotically stable, and Lyapunov system will tell that now for nonlinear stability also everything is justified, so it will be stable. So this is what happens. So this is just picture show that as you add damping, they go inside the unit circle, so the stability region become asymptotically stable region. So and now all results are valid for the non-linear system as well. And this is just a picture how it looks like. So for different delta, as you get damping smaller and smaller and smaller, these zones, they approach the zones of the system without damping. So essentially, this justifies why the white region is stable, because as you add very small damping, they become asymptotically stable. And then we have no problem with non-linearities. Okay, so this is, I think this ends mathematical part. So let's go to applications. Applications will be, okay, I go to applications to the questions. I will not show experiments if you don't ask questions. Oh. Previous. Yeah. So I will come to this. Okay. But your question does not count. Yeah. Yeah. So, but I will exactly come to this question for the application part. Yeah. Okay, I'll wait. I'll just. So why A can be positive, by the way? Can you think? So the diagram is shown for A negative and positive. Remember what is A? Yeah, A is natural frequency. So A was G over L, which is natural frequency, and divided by omega square. So when A can be negative? Any guess? Yeah, so A can be negative when J is negative. So if the gravity is not pointing downwards, but pointing upwards, it changes the sign, so A becomes negative. And it's the same as a vertical position of the pendulum, because for the vertical position of the pendulum, gravity points in the opposite direction. So A negative corresponds to exactly the same pendulum, but if you linearize it near the vertical position. So we come to this. Okay, so this will count. Okay, because so the applicational part is actually very simple. So as you can see, this A and B. So the stability diagrams, instability zones look like this. So this is 1 force, 0, 1, and so on. So really the instability region, the thick instability regions is near 1 force. Near 1 and so on, they're very, very thin. So they become thinner, thinner, and thinner, and thinner. And also if you saw the diagram with a damping, as soon as you put some damping, it pushes it up. So essentially, it's very hard to observe this instability, not very hard, quite hard to observe instability, and almost impossible sometimes is to observe other instabilities. So the really instability you see is near 1 force, because there the region of instability is big and thick. So let's see how it works with the damping. You see, so this is the first, and almost very weakly affected by damping. But second and third, you should put a huge amplitude in order to enter, because a very, very small damping already pushes it up. So, and what does it mean this first instability zone is A equal 1 force. What is A is there, so it's G over A is G over L omega square. And from this we can find omega. So this is A, let's say it's not 1 force, it's near 1 force. No, this zone is near 1 force. So omega, you put it here, 4 comes here, and you take square root. 2 times square root of G over L. So this is the frequency of a pendulum. So this is natural frequency of the pendulum of these oscillations. So the instability occurs if the frequency of the support is twice larger. And this is exactly those videos that I saw. So the man has to, that in this huge, remember he was sitting with twice larger frequencies. So every half period of the swing, he was sitting. So his frequency was double of the natural frequency of the pendulum. And essentially all applications of almost all applications of parametric resonance are about this ratio, 1 to 2, because this is the main zone of parametric resonance comes from 1 force, and it corresponds to this ratio between the natural frequency and excitation frequency. The excitation frequency has been double of the first. There is also direct resonance where they're equal, but it's much thinner. So if you sit with smaller frequency, it might be not so useful. Okay, so this is the first application, and okay, let's take some video. Well, I will show a video which is nothing special really, but good to see how it works. So these are videos from when I was in laboratory of Hiroshi Yabuno in Japan. So this is, he gave me this video. So this, actually they measure and very, very nicely all the motion. So what you see is, let's see it from the beginning. It's actually, it's like a swing, but here you can see it very clearly. So you have a support moving, you have a pendulum, and when it starts to move, so you can see the support make a full period when the pendulum just have a half period. So pendulum goes left, it's already make a full motion. You see, every time pendulum make full swing, so left and right, the support make two jumps. And this is parametric resonance, so you can just see it exactly. Should put on the sound. Oh, there is a. Okay, so let's go to the. We already saw many videos here, so let's go to another case, which is A negative. So as we said that A, so we already have this A equal J over L omega squared, and B equal delta, which is amplitude of the support oscillation over L. So when A is negative, so A is negative means that G is not pointing down, pointing up. Or if you look at the upper position of the pendulum, it's exactly the same situation. So you consider the pendulum and the gravity, respective to pendulum, gravity looks up. And now you shake the base. So here the problem is opposite. So the equilibrium was stable. Right? It was stable. So all you can do with this equilibrium is, well, it was unstable. Well, we know if you put pendulum in upper position, it falls. So what we can do in principle is to stabilize it, to make it stable. So the question whether it can be stabilized or not. So I have to redraw this picture and just draw it for negative A. So I did not make it nice. Exactly. So it's A, B, 0. So the positive A is lower part of lower equilibrium, negative A is upper equilibrium. And so this is somewhere here is one force, and then there is this huge zone of instability, which penetrates to the negative A side. And then in here there is a parabolic instability zone. So can we make it stable or not? So what we will change, let's fix amplitude and change just frequency. So if you just change frequency, which means that B is constant, whatever positive, and A is changing. So what we see that whatever B is, for very small region, but never 0, there is a stability region. So you can stabilize the pendulum in the upper position. And now, what does it mean? That the pendulum, the upper equilibrium of a pendulum, this system is often called Kapitsa pendulum. because Kapitsa, though the results of Kapitsa were not new, but he put quite a lot of attention to this problem. So the upper equilibrium of a pendulum gets stable. As A goes to 0. So it is goes to 0. I'm writing like this, so it's increasing from negative values to 0. And what means A going to 0? So you cannot change gravity. Also, it's quite hard to change length of the pendulum much, but you can easily change frequency. So all you need to increase frequency. So i.e. for sufficiently large excitation frequency. So there is a threshold which is given by this left boundary. So if the frequency is higher, you're in. So smaller amplitude just require even higher frequency. So if you can shake the pendulum fast enough, you surely stabilize upper equilibrium. So let's see how it works. So it's also from Yabuno. This sound is good. Should just become stable. And somehow this is rather general phenomenon. To study it well, actually you need to some extension of this business, like averaging theory and non-linear analysis. But anyway, it all goes in this direction. So even if the system is much more complex and you have infinitely many degrees of freedom, it has a tendency that the unstable equilibrium become stabilized by high frequency. So let's see some slightly more complicated example. So it's Kapitsa beam. I don't know if you see. There is this very thin, you see? Very thin rod. Oh. If you don't see, you imagine. So there is this rod, it oscillates, and you see just by changing the position of the support, you stabilize it in the vertical position. So it's infinitely many degrees of freedom, elastic system. Well, I will show this video just because it's nice. So you can do something different. So you don't need to put it excited vertically. You can excite horizontally. It will be just behave something in a different way. So it's not covered by this theory, but anyway, it's nice. So we'll excite it horizontally. And so at the moment it will lose stability. So now we destabilize the vertical. Boom. And so you destabilize the lower position, put it up, and then it becomes Kapitsa pendulum. you can go much further. So let's see. So these are experiments from laboratory of Blechmann. So you have two, just wait. How to make full screen? Ah, okay, doesn't matter. So you have two balls. Well, important that one is elastic, another not, but for us it's just when it's not elastic, there is no effect because there should be some force. So you put them into the water and they, let's stop. So they both slide. Yeah, so since they both slide, they will float. So in order that they don't, so you see it well, they put them on, they put the string just to, so you see control the height. So the idea is you'll shake it, you know, with high frequency. So what can happen? Yeah, so this is the only can happen, no? Because it's the only thing that can happen. Certainly you have to do it with a strong force. So this is St. Petersburg, so you see machinery is pretty tough. Unfortunately, the camera is not so good, so you need to reach the right frequency. When the frequency will be above threshold, the one which feels the perturbation, which will be one which is elastic. It will, you see it dropped. I know they also tried in opposite. They tried to put a heavy ball and go up, but it kind of worked, but not very conclusive because it turbolizes too much, so they could not make it very nice. So. Okay. This was very nice PhD of Sergei Sorokin. Okay, so now we go next. So we go to the next, which will be it will be not mechanical, but physical application. So far, what we tried is we know that we can stabilize, we can destabilize the equilibrium by parametric resonance, and we can stabilize unstable equilibrium by the same effect. So what if you want to make both? So may like to make both. So you destabilize the certain equilibrium and stabilize the others. So and actually it's a different question. So the physicists, especially in quantum physics, they want to make experiments. They want to make experiment with a particle. In order with atom, with molecular, whatever. In order to make experiment with one molecular, it's a problem because it's always in a matter. So it's even in a gas, it always hits the other molecules. How you know that you do experiment with this molecule? Absolutely impossible, no? Because there is too much noise and so on. So you need to take this particle and put in certain place in a space, so you know where it is, and there is nothing else. And then if you know it's there, you start to make experiment, you interact, making some, I don't know, put a laser and then measure what happens. So this is the question, how to stabilize the particle in certain place. So in this case, we will think about charged particles, so like ion, so there is some charge. But the only way you can affect the particle is an electromagnetic field, but there is a theorem that if you put static electromagnetic fields, it cannot have a stable fixed point. So you cannot stabilize particle in any place by static electromagnetic field. But you can make it periodic. So if you do it periodic, we know that you can stabilize, but we don't want to stabilize everything, yeah? Because if we just stabilize, all particle will stop. But we won't just stabilize this particle, not the others. So we have to combine stabilization with destabilization in the same apparatus. So this activity started. I think it started in the 50s. So what they do? Let's clean. Keep this. I surely can erase this. You don't see, no? You don't see. No? I'm sorry. So now I can move it. So why you should do? Better? No? Sure? I don't need the full board. So what we do, you put two fields. So you take a particle, which, let's say, 2 dimensions, which is x. It actually will be just a horizontal plane, and then there will be vertical z. So you can make one field which, for which the horizontal motion is Mathieu equation. So for horizontal motion, you take x max. So for horizontal motion, it will be Mathieu equation, x dot plus a plus b cosine tau, x equals 0, with certain a and b. Well, in physicists also they know tricks very well. So they make magnetic field with some, I think it's hyperbolic form. So it's not sine or cosine, it's exactly x. So you don't care about nonlinear effects. So you can make a field in such a way that it's exactly linear equation. So it's a field exactly linear, gives exactly linear the Mathieu equation. And then for z direction, you do the same, but now a and b is just properties of the field, so you can make a negative. Okay. So essentially what these two equations will make is the one will make it stable, another will make it, some particles will make stable, another is used to destabilize. So one is used to stabilize, another used to destabilize. So it's important to know what are the parameters. So remember, in this case, the parameters were g over L omega square. So the essentially important is that A is divided by some constant divided by omega square, and B is some constant. And the important property for the pendulum is there is no mass, but there is no mass because it's gravity. So gravity is gravitational force is proportional to mass, which means that mass cancels from equation. But for the particle and electromagnetic field, the interaction is proportional to charge. A charge is fixed. So mass will not cancel, mass will come here. Mass will come into the denominator because the mass will be on the acceleration term and there will be no force mass in the first term, so mass jumps in the denominator. So since this force is proportional to charge, you have A as some coefficient A, which is coming from the shape type of the field. And what is important is inverse proportional to mass, and it's still, you have this omega square. And for B, it's a constant, but again, we have mass below. So now what they did is shown on this picture. Well, this picture is turned, so I will redo the plot. So it's our plot by turned 90 degrees. So let's go back to the original directions. This we don't need, no? So when the particle will be stable? So the particle will be stable if it must be stable in both coordinates, right? So if it's unstable, either in x, it will fly away in x direction. If unstable in z, it will escape in z direction. So it must be stable in both directions. So stability diagram for the first we know. So there is this tongue which starts at 1/4, 0. So there is this. So this I will always. So it's poof, and like this, boom. No. So this is a stability region inside. It's stable inside. So now, so this is for x. X stable. To be y stable, we need to draw the same, but for a negative. So it was a nice green color. Since a is with minus, so stability region is just you just flip it, no? So this is y stable inside. No, z stable, no, this vertical direction. So finally the stability region is what is an intersection. What was the red color? So this is stability region. Okay, so what the lower pictures show is how we can pick up the parameters in order to stabilize just the particles when we want. So I will repeat this. So the A is coefficient by m omega square, and B is B over m. So this is a static part of the field. This is periodic part of the field. So first, let's put B equals 0. So B is 0. So when B is no. A is 0. Let's put A 0. So this is just for you to understand how the geometry looks. So it's not something. So if A is 0, then this is 0, and then depending on the mass, your particle will be in some point, right, on this B axis. So if mass is large, B is small. So these very heavy particles are here. This lighter particle is here. Some lighter particles here. Some lighter particles here. And if the particle is heavy enough, it enters, it's stable. So you at least the particles too light, they will escape. But now you increase B, this B. So for any b, all the particles, they will be on a straight line. So you see, whatever m is, ratio between a and b does not depend on mass. So the particles all on a straight line. So what you can do, so by changing, for example, frequency, you can stretch it or compress. So you can put this particle, I like this particle. So I can put it whatever I want, and then I increasing A, I turn it to the side. So instead of being on this line, they can be, what we do, they can be at this line. So this is heavy, lighter, lighter. No, will be here. And then we put it inside. So we can make a geometry in such a way that there's only one type of particles are stable and all others are not. So this is a way how by easily tuning the parameters, you can throw the beam of particles where you know that some particles are those that you know, but it's very hard to, from the beginning, to filter them from the others. But you know, all the others will escape, and only those will be there. Only those with the right mass, and essentially, if you are with iron, with exactly specific iron, so you can draw this line very, very close to the angle, so it's only those very precisely these particles will stay, all the others will escape. And this is the way how they made, they learned how to put just one single atom, molecule, and so on at the right position in the space and make experiments. So now they can even do, they can make a crystal, so they can put, what, I don't know, 100,000 particles in the right positions on the space and do experiments. And the nice thing is that, so I said it was so influential that in 1989, these two, Professor Hans Demelt and Wolfgang Paul, they got Nobel Prize in physics for this kind of development of this apparatus. And what I really suggest you is that you open the paper of Wolfgang Paul. It is a paper in, it's a paper in Modern Reviews of Physics of 1990. So this is a Nobel Prize lecture paper. So he made a Nobel Prize lecture and then wrote a paper. So electromagnetic traps for charged and neutral particles. And you can now fully understand it, because if you see the theory, essentially the full theory are these two equations, which is Mathieu equations. One with positive sign, another with negative sign. And all the rest is just technology. So there is no more science. So the rest is, you see, it's this intersection of the instability zone, which is called the Einstein diagram. So this is it's a very old diagram, which is known for more than 100 years. So after 60, 70 years, they applied it. So the rest is experimental results. And they could make quite unbelievable things. So you can just put particle and with the parametric resonance. I think that's all. Huh? Okay, I know you don't have questions, so so that's all. questions? Okay, good. Well, it is become a disaster. Yeah. That's already two different. Well, if the frequencies are in a rational relation, you can still do it because you just find the common divisor. No, but if they are what's called incommensurable frequencies, then it become a it's called quasi-periodic excitation. There are results, but it's really far from being well. From mathematical point of view, I don't know much results in this direction. So it's actually a good thing to try and to see if it applies, but mathematics do not go too far in this, so unfortunately. So essentially, this is a most complicated case, more or less, where we really can go understand most of the things, at least from point of view of stability. From point of view of nonlinear dynamics, it's maybe very complicated because it become chaotic and all of this kind. But even from point of view of stability, if you put two frequencies, this is already trouble. So there is no theory which will just tell you how to get an answer, because you don't have eigenvalues. There's no way to get eigenvalue from them.
Let's thank again Professor Alexei Mylibaev for his very enlightening and exciting lectures. And I'd like to give to Professor Alexei a souvenir from Escola Politécnica. This is also part of the souvenir. It's just a pin for you to use in your jacket, okay?
Oh, thank you very much.
Most welcome.
Okay, thank you everybody for the participation.
Right, and now I would like to ask Guilherme Franzini to give you some announcements regarding the visit to the lab, okay?
ABCD, lá no ABCD, são grupos 1, 2, 3. Estou combinando com eles primeiro. Calma. Grupos 1, 2, 3, 4, 5. No TPM, ABCD. NDF é o E. O A, sala de realidade virtual. O B se dividiu agora em B1 e B2. Que é Full Mission e Crane. O C continua sendo Domo. Tá? O D continua sendo o tanque oceânico, que se divide em D1 e D2. Certo? E aí o NDF vai ser o E, vai se dividir em E, e o pessoal tem que esperar, porque só pode entrar 12 de cada vez também.
E onde que é esse Crane?
O Crane é do outro lado. O Crane é subindo. Subindo primeiro andar, do outro lado. Não se preocupa, já falei, acabei de sair de lá. O Tanuri já organizou tudo. Vai ter um cara guiando do B1 para o B2, do B2 para o C. Aqui precisa ter um aluno para cada grupo. 1, 2, 3, 4, 5. E só isso. E lá eles têm um cara para fazer o rodízio, para guiar o rodízio, e um em cada estação. Então eles têm estações, um número suficiente para cada estação e mais um que vai indicando o rodízio, tá? Então eu vou explicar isso daqui, tá? Vou explicar. Eu cheguei, né? In time. Just in time. Hello. Good afternoon. Just to organize our visit, because we have We have 2 laboratories, 2 distinct laboratories, 2 buildings, and we are more than 120 people here. So we are going to divide the groups in 5. And building 1, I'm going to sketch this. In building 1, that is TPN, we are going to have 5 distinct visit stations, all right? Actually 4 that will be split, 2 of them will be split in 2. And at NDF, that is the Nucleus for Dynamics and Fluids, there's the water channel facility. In the other building, we are going to have another visiting station. So let's try to sketch this. We have TPN. TPN is for numerical offshore tank. In Portuguese is tanque de provas numéricos. Okay, for those who speak Portuguese. All right. Here we are going to have A, B, C, and D visiting stations. This one is a virtual reality room. Actually, it will be a film on, an institutional film on the research that it has been doing all these years at TPN to give you a grasp of offshore engineering and offshore mechanics. B is a simulator. We are going to divide in B1 and B2. This is a full mission simulation room, and this is a crane dynamics simulation. It's an offshore crane dynamic simulator, all right? That you are going to see. A very nice nonlinear pendulum. All right. Then this is what we call DOM. That is a complete simulator with about 270 degrees of visualization, all right? And after that, D will be the ocean basin itself. Here we have D1, that is the wave experiment. When I say wave experiment, of course, it's free surface wave experiment, right? We're talking about an ocean engineering laboratory here. And the second one, that is D2, will be a parametric excitation experiment. Both of them are set up, are mounted in the same facility, in the same room, okay? So, group number 1 is going to start the visiting in room number 8. Group number 2 will split in 2, okay? So this will be G2 1 and G2 2. And so on, all right? Group number 5 will start the visiting at the other building, just across that channel, okay? That is in the mechanical engineering building. So we have to go and come back. The only group that is going to cross this channel just once is 5. Very good, logics. Okay. All the other 4 groups will go to cross the channel twice. All right? Oh, yes. At each visiting station, there will be an operator and a guy, a student, or an engineer that is going to explain what is going on. Actually, they're all demonstrations. There's no measuring that is doing at this time, all right? Just for demonstration. Okay, and each group will have one leader, yes, one leader. That will be a student from our laboratory here, that will be identified with the vest. All right? Those guys, please stand up. And who is the leader of the leaders? Giovanni is the leader of the party. Okay, the party is leader. All right, so there will have to be 5. Where is the 5th? Oh, you are not in a vest. Please. Yes, please. Okay. Who is number 1? Giovanni is number 1. Who is number 2? Guilherme. The ladies, 3. 3 for Leticia and 4 for Pauline. And 5 for Vaguinho or Victor. All right? Is that okay? Quite well understood, I suppose, right? All right? So these guys are the responsible for you to not fail in the channel as well. And they are responsible also for the security issues, okay? Of course, in every laboratory, you have things that you cannot do. For instance, step on the flaps, the wave generators, never touch them, all right? Buttons, please do not try any button. You don't know what can happen, all right? So, be just engineers. Think safe side all the time. Do not, at this time, do not be scientists, all right? No curiosity. Curiosity can kill, all right? You could, just by thinking, and questions will be allowed. Of course, we have to be very well organized, and the timing is quite important because we have around 2 hours to do all these things, okay? And we are, this I think that's the largest visit in TPN that they have. I think that the largest one, for sure. So we have to be very well organized and don't switch. If you like very much cranes, for instance, you cannot stay in the crane station, all right? You have to switch, all right? Okay? You're obliged to do that. And we are going to, those who break the rules will not get the certificate. All right, okay. Is everything understood? Guilherme made a tremendous job in organizing all things, and the guys who organize also the experiments and everything. I think that we have to thank them. And Guilherme, how are you going to devise group 1, 2, 3, 4 in alphabetical order, right? So you already know what group. Group 1, please raise your hands. Who is group 1? Who is group 1? Okay. What? Let me see. Guilherme, please help me here. Group 1 will be up to? Up to? That didn't. Group 1. Avelina Raman. No, you say the last one. You say the last one.
Avelina Raman to Ciro Martins.
Okay, from Avelina to Ciro Martins.
From Cristiane to
Fala para mim, eu repito. Group 2 from
Cristiane and
Christian to Ícaro, okay? Up to Ícaro. First name, not last name. Third group. Idin or Idin? Is Idin or Idin? Idin. Up to
Marcos Vinícius.
Marcos Vinicius. Group 3. Group 4. Maria Aline. Up to Rosvando.
The remaining group number 5.
And all those not mentioned will be group number 5, of course. And our invited lecturers have to choose one group to start, all right? So Alexei is going group 1. Is that okay for you? Alphabetic order as well? The lecturers are the only ones who can choose. What do you want to the ocean basin? Okay. So is group 1, 2, 3, 4. So you're going to start with group 4. Professor Standel. 5. So you are in the other building across the channel, okay? We call this channel, this very small channel, we call it Tejo River. Tejo River, the Portugal. Yeah, you have some Portuguese here, right? Raise the hand. Yes, we call it the Tejo. I don't know why. Because that part is Alentejo, okay? And this part is Lisbon, this kind of thing. All right. And who more? Paulo, please. No, 5 is Alec. No, 5 is already Stendhal. Group 3 for Paulo, okay? And who more? Mazzilli? Number 2, okay. And number 1. Where is Stefano? Okay, Stefano is going to start with group number 1. And Livia, where is Livia? Is not going to visit. Okay, all right. And Franzina and myself, we are going everywhere. It's a kind of uncertainty principle. Yes. Get that? Okay. All right. So to start with, we can start. Okay, just a very quick coffee break. When I ring the bell, you have to move, okay? All right?